once again belatedly welcome you all to the University of Michigan. The University of Michigan is the #1 public research university in the country. And with that comes about $1.5 billion a year the university spends on research. And they have a very strong focus on interdisciplinary research, which is incredibly important as we move forward with complex problems that the world faces. Within the U of M, I also want to welcome you to the School of Public Health, which is one of the top schools of public health in the country, as well as one of the most well-renowned departments of biostatistics. In addition to biostatistics, we also have 5 additional departments: epidemiology, environmental health sciences, health behavior and health education, health management and policy, and nutrition sciences. And if you got to know any of the students or faculty in biostatistics, you probably got a sense that many of them work with folks in those other departments and in other schools within the university. So it's a very vibrant research community here. The fact that this year's symposium is on Zoom, as opposed to in a fancy university auditorium like it typically is another testament to how important it is to be able to effectively not only analyze, but also communicate effectively complex health data. As we all seen in the past year and a half, it is crucially important, and we're going to continue to see these types of problems arise, and the need for data scientists and others to come together and provide these analyses and communications. If any of you follow Dr. Mukherjee on Twitter, you might know that she's been battling this for the past year and a half with a focus on what is going on in India. So I would recommend, if you're not following her yet on Twitter, to go ahead and do so. But in general, we have vast and increasing amounts of data are being collected, and they're being collected in means that continue to grow in their diversity and how they're collected, which brings about many issues with regards to data harmonization, ethics, and all sorts of other things that you've probably been exposed to in these past few weeks. But what we're going to need is bright young minds like yourselves to come together and be able to address and effectively communicate and analyze these complex data sets to tackle these very complex problems we're going to see going into the future. And what that does is the goal would be to effectively inform policy, whether it be at the national or global level, at the state level, county, clinical, and even personal decisions for individuals as they go about their lives. Hopefully those can be informed by science and data. I also wanted to make a point that hopefully you got a chance to meet some of your peers and get to know them. I think these relationships will be key for professional networking moving forward, but also many strong friendships can really develop out of programs like this. And I don't want to take a lot of time today, so I know there's a busy and important agenda, so I'm going to go ahead and wrap up. And I just in closing wanted to really thank Dr. Mukherjee and the staff, faculty and students that she mentioned earlier in really bringing together this very successful program. And I have all confidence that it's going to continue to be strong in the future. So with that, welcome again, and please enjoy the symposium. Thank you.
Thank you so much, John, and thank you for sharing your time, and thank you for always supporting BDSI, and you have been a speaker and welcoming the student for the last 5 years. So thank you, and we cannot do this without the school's support. With that, I'm going to hand it over to Matt, because Matt is very good at timekeeping and disciplining, and he's going to coordinate the presentation by the project group. So over to Matt.
All right, thank you, Bramar. So welcome to the highlight of the symposium. With all due respect to our keynote speaker, when our students get to talk about the research they've done, that is the highlight of BDSI, and a highlight for everybody who's worked at BDSI to get these students where they are. And I want to echo the comments that have been made that to see what people have been able to accomplish in this remote format, that the fact that we've never been in a room together, we've learned how to code through R, we've handed you complicated data sets, and you've made it work. And this really is of all the BDSI symposiums, this one is different for many reasons, but certainly something special. One of the things that makes it very special is the fact that you've accomplished so much overcoming this challenge of the remote format. So I will introduce each group, and I have a little stopwatch here, and I'm going to try to keep track of you. So 20 minutes. I know that you have a lot to say because of all the work you've done, but I will step in if we start going over. But do your best. So we're going to start with the imaging group. You go ahead and share your screen.
Alrighty. Hi, everyone. We're the imaging group. My name is Michael Miller. Our faculty mentor is Dr. John Kong. Our co-mentor is Zakai Lin. And I think everyone else is going to introduce themselves as we go. So, yep.
So our team is working with imaging data from the ABCD, or Adolescent Brain Cognitive Development Study. This is the largest long-term study of brain development and child health in the US, with 21 study sites and 11,878 subjects between the ages of 9 and 10. The study focuses on neurodevelopment and behavioral maturation. These results will provide us with practical information to promote the health, well-being, and success of children.
The goal of our project is twofold. The first being that we want to identify the subgroups, of which there are two, so this is a binary problem. And the second being that we want to figure out what brain regions and functional networks are associated with the children's cognitive IQ score. The data we are given is fMRI time series data, which is organized in regions of interest. So each region of the brain, of which there are 333 that we are looking at, and the functional subnetwork, which is the groupings of these regions of the brain. We're looking at the Gordon parcellation for this project. The data is then organized into the training set, the validation set, and the testing set for us to utilize throughout the project.
Hello, my name is Andrew Zhang, and I will be presenting with my group mates, Ramadan El Nil and Zachary Qian. Next, please. So our project involved a two-stage approach modeled around the two goals of the project, which are subgroup detection, followed by the formation of associations between brain regions and the response variable of IQ. So the first of these stages accounts for the differences between those two subgroups. And that is to say, subjects within each subgroup are known to exhibit similar types of associations between IQ and imaging biomarkers, such as activity within brain regions and networks. So we explored 3 regression models in the second stage of biomarker association because we wanted to use a sparse regression model, which the GLMNet library in R is pretty well suited for. Next, please. So our project workflow really begins with raw fMRI images, which were then processed to time series data. We constructed a functional connectivity tensor and used this tensor to compute the local clustering coefficient for each individual brain region. So for the first stage of subgroup detection, we trained models using random forest and logistic regression to predict subgroup labels from functional connectivities. We then use this model to predict subgroups using the validation data before splitting the validation data by those predicted subgroup labels. We also computed the mean of each time series and split these mean values by predicted subgroup labels as well. And for the second stage of biomarker association, we used lasso, ridge, and elastic net regression to build models to extract the brain regions that were the most significant predictors of IQ. Okay, next, please. So these fMRI time series data were collected for 333 brain regions, and we wanted to measure the connections between these regions. And we achieved this by computing correlations between every pair of regions for each subject in the training set, and then reading those R values into a functional connectivity matrix. And you can think of this matrix as an adjacency matrix in an undirected graph. So we then applied a Fisher transformation, which maps the sampling distribution of the correlation coefficients to an approximately normal distribution. And finally, we proportionally thresholded those resulting values to reduce noise. Okay.
So the next step is to select the features for our subgroup detection problem. And so for our subgroups, we opted for the node-wise local clustering coefficient for every single region. And so the justification for this is we want to reduce the dimension of our high dimensional data while still maintaining excellent generalization of these data. And so another also thing is to note is that previous literature supports the use of network statistics for resting state fMRI. You can see this in Kazi et al. 2015. They uses small worldness, another statistic, to predict Alzheimer's. And then Telesford in 2010 also goes over an array of network statistics used in fMRI networks. Next slide, please.
So to predict subgroup labels, we built 2 classification models and tested their performance using training data. We chose logistic regression and random forest instead of deep learning techniques because we valued interpretability. And so for logistic regression, our confusion matrix achieved 100% accuracy and a k-fold cross validation accuracy of 83.7%, while random forest resulted in 91% accuracy and 90.2% accuracy respectively. Next, please. Here we have 50 brain plots for logistic regression and random forest, showing the top 50 most significant regions included by each model. And the regions are each assigned a color based on the level of statistical significance. Next. We found that these 6 highlighted regions of interest provided the most important features in predicting subgroup labels between our 2 models. Next, please.
So the second stage of the biomarker problem is a regression. And so in this case, we use the mean activation for every region across all time points as our feature to measure general cognitive ability. Previous literature has demonstrated that resting state activation in fMRI time series, as well as brain activity in time series, are both related to intelligence and general cognitive ability. Another quick note is that we selected the top 50 features from each of our best models to more closely interpret and analyze. Next slide, please. So here we see a table showing our regression performance for each of our models and for each subgroup and classification method. And so observe that all these methods that we implemented exhibited relatively good performance, never exceeding an RMSE of 2.83 and always fluctuating around 1.9 to 2. We see that for lasso, logistic worked best, whereas for ridge regression, random forest did, and elastic net had a blend of both. We attempted these methods exhaustively by the nature of being an exploratory project, and the works of Professor Hasty and Tip Shrani from Stanford are very good for selecting these pertinent features. Next slide. And so here's a table of the brain visualizations that indicate where the important biomarkers associated with general cognitive ability are. We see that in general, biomarkers are pretty consistent across each subgroup, regardless of model implementation, which thereby validates our findings and eliminates any type of that type of variation between features. Next slide. And so these upcoming next 2 slides are more or less just supplementary figures to show the consistency of the important subnetworks in each subgroup. And so for subgroup 1, we have these 4. And then for the next slide, we can see subgroup 2s, which are these 4, which we'll go into detail in the next slide. And so after modeling cognitive ability and detecting subgroups, we arrive at effectively the most important aspect of the project, the biomarkers. And so for group 1, we see that the default mode network, otherwise known as DMN, the control network, and frontoparietal networks are the most important in terms of predicting general cognitive ability for group 1, and control and visual subnetworks for group 2. So this agrees with the previous literature seen in Dubois et al., Schultz and Cole, and Yoon et al. And so this is more or less to show that these networks were consistently detected by 3 different approaches. And in doing so, we have also found novel findings in the parietal, occipital, dorsal, and ventral attention subnetworks, as well as detecting a large difference in the somatosensory networks between subgroups. So thank you, that's group 1.
Hi everyone, my name is Izzy and I worked in group 2 with Emma, Chloe, and Judy. So the way that our group approached this project was to try 4 different classification models on the training data that would classify the regions into either subgroup label 1 or 2. So our model selection criteria for choosing our classification model was based on the accuracies of each model on the training data set and the mean square error from the linear regression on the validation data. The 4 models our group attempted were k-means, clustering, random forests, logistic regression, and naive Bayes. And as far as our inputs, they were very depending on which classification model was used. The naive Bayes and random forest methods used the ROI region of interest mean time series data, which is the mean time series of each region for each patient. The logistic regression used proportionally thresholded data that kept the top 40% strongest correlations, and the k-means used the raw unthresholded time series data. And this model selection process can be visualized on the next slide. So as you can see, we started out with our 4 classification models that were tried on the training data, and the accuracies for each were computed. And since it was determined that the 2 most accurate models were logistic regression with an accuracy of 88.6% and k-means with an accuracy of 89.7%, these were the 2 models that we used on the validation data. And then on the validation data set, the k-means model gave the lowest mean square error from the linear regression. So therefore, it was determined that k-means is the model that would be best at predicting the subgroup labels and therefore predicting IQ in the testing data set.
Okay, hi everyone, I'm Judy. As Izzy just talked about, the model we chose to use for our regression was k-means, and we chose it because it separated the data into clusters that matched the subgroups really well with an 89.7% correlation. And one thing we think is really important to point out is that we were able to use the entire functional connectivity matrix, even unthresholded, meaning that we used all the raw data rather than network statistics. And the raw data is what provides the highest amount of information. So we didn't lose any meaningful information that could have been lost if we did use any network statistics. And so the images on this slide show the average functional connectivity matrices for the 2 groups found by our model. And we can see a clear difference in the connectivity patterns of the 2 groups. On the right-hand side with subgroup 2, overall, the people have many more strong connections between different brain regions compared to the brains of the patients in subgroup 1 on the left. And we can see that visualized in the next couple of slides.
So moving on to our linear regression problem, as Izzy mentioned, we used the mean of the time series data for each ROI, and this is because the original data has a 333 by 334 matrix per patient, which is a little too much information for us to put in a linear regression. So we did the mean, which allows us to decrease this to a vector of length 333 for each patient, 333 being the possible regions of interest covariates. We then performed backward selection on these possible covariates to limit it down to what was really useful for the linear regression. The results were that subgroup 1 used 167 regions of interest and subgroup 2 ended up using 195 regions of interest. This is visualized on the next slide. So the brains for subgroup 1 and subgroup 2 are both shown here with their covariates. And as you can see, there's a pretty strong difference between the 2, which lines up with the functional connectivity matrix that Judy showed 2 slides ago. So for each linear regression, we got a multiple R squared for subgroup 1 of 0.96 and a multiple R squared for subgroup 2 of 0.98. So we found that these models were pretty accurate, and this is where we decided to stop and then use this linear regression on the testing data. As well as with k-means, we got a mean square error of 0.93 for subgroup 1 and a mean square error of 2.56 for subgroup 2. There is a pretty large difference between the 2 different subgroups and the mean square error, but we've accounted this to the fact that the variances in the IQ for each subgroup is pretty large, subgroup 1 being at 11 and subgroup 2 being at 19.
Hi everyone, I'm Chloe, and here you can see which regions are significant with IQ. So the color of the regions on the right matched the nodes on the left. In group 1, the significant regions were DMN, parietal occipital, and the control network, which is represented by both the pink and the blue. And in group 2, the significant regions were the control network, dorsal attention, ventral attention, and visual. One note is that group 1 does not have any ROI in the medial parietal, and only 1 ROI in salience and auditory, whereas group 2 does not have any ROI in salience and only 1 in the medial parietal. The salience and medial parietal are relatively smaller regions, so this isn't that unusual, but auditory is bigger, so this could be something to look into moving forward. Hi, my name is Laura Davis, and I worked in subgroup 3 with Joy Huang and Michael Miller. So our group used 2 models. The first was used to predict which subgroup the data belongs to. And then using those probabilities, we use another model to predict IQ score. We use time series features and network stats at the ROI and FSN level. And our goal was to test the associations between these specific features and IQ, because although other features had more predictive power, ours were widely studied in literature. We used Bayesian methods with STAN and R because it allowed us to easily code Gaussian process priors and rich regression priors together. Next slide. And here are the features we looked at. So sample entropy is the unpredictability of voxel signals. Variability refers to the volatility of neural signaling with regards to information processing. Next, transitivity is our clustering coefficient. And then we also look at strength, which is the weighted vertex degree, and also edge density.
Hi, so a quick note about Gaussian processes as priors that because ROIs have spatial locations, we'd expect the parameters associated with those ROIs that are nearby to have similar values. And we expect those values to vary smoothly as you move across the brain. We use these as priors because they help us pool information across parameters whose ROIs are spatially close. The overall look at our framework is that the classification model we used was logistic regression, and we used these to predict the probabilities of each individual belonging to the subgroup, the second subgroup. And then in our 2 regression models, we were predicting IQ. For the first one, we just used the predicted subgroup probability as a feature, whereas in the second model, we used the predicted probabilities as the mixture probabilities in a linear mixture model. So each group would have its own Gaussian component with varying means and variance parameters. For all of the models, Gaussian processes we use as priors for the ROI level parameters, whereas ridge regression priors we use for the network level parameters. The specification for our mixture model is given here. Again, pi sub L2 is the probability that the Lth individual belongs to the second subgroup. And see that the means and the variance components are different. In particular, the network level parameters vary between the 2 components, whereas the time series parameters are the same between the components. We did put Gaussian process priors with distinct covariance functions for the entropy and variability parameters. And one table of results is given by the 95% credible intervals of the entropy and network level density. The data was centered and scaled, so in a sense, these do kind of capture effect sizes to some extent. And one takeaway from this is that the effect sizes with the network level features were actually much larger, and this is relevant when determining the practical significance of various features and their relationship with IQ.
So I'm Joy. We analyze the data for significant regions associated with IQ. On the right is a brain network visualization for entropy features. So the significant effect sizes of the region are determined by a 95% credible interval, does not contain 0. And so the bigger the node, the larger the effect size. For entropy features, we observe some effects in the auditory and DMN regions. Next slide, please. So what we observe is consistent with existing literature. This paper concluded that the relations between brain entropy and IQ is most strongly observed in the prefrontal cortex, temporal lobes, and cerebellum. Our data observe effects in the auditory region, which is in the temporal lobe, and DMN region, which is in the prefrontal cortex. Next slide, please. We also analyze the data for significant connections between functional subnetworks associated with IQ. On the right is a brain network visualization for density features. Here, the nodes represent the function subnetworks, and the edge represents the significant effects observed between the 2. The heat map on the left displays the effect size. The darker the color, the bigger the effects. We see how the most significant pair connections are singular or perk R to ventral attention to parietal occipital, and medial parietal to frontal parietal. These connections are interesting to further explore, especially because density analysis is used. Next slide, please. We got significant posterior distributions for subnetwork density. And density is good for inference and has been used as a measure of functional connectivity for a variety of brain disorders in past literature. Next slide, please.
And so lastly, we added a discussion section because by nature of the program, there wasn't enough time for to implement some of these ideas. And so some examples are for pre-processing, implementing ICA, otherwise known as independent component analysis, which is effectively, it separates multi-signals into additive subcomponents. And so in the context of our project, it denoises voxel-based data prior to actually constructing the regional time series matrix. For feature selection, since we're dealing with time series data, using an ARM or autoregressive model is very popular. And then for regression, two methods, generalized scalar on image regression would have been a very interesting method and approach to the project. It would account for the 3D nature of brain imaging data, as well as using a joint modeling method to reduce the effective classification error contributing to regression error. It's basically using some of the ideas that Michael's group had actually used Bayesian methods and just using a prior for the subgroup classification. So it's a one-stage one. Thank you for your time. A special thanks to Professor Kong and our GSI, Zakai. Thank you.
All right, thank you from the imaging group, and stayed right on time too, which was amazing. Didn't even have to step in. Do we want a minute for a question? Anybody? Any quick questions from the audience? So you're getting imaging group. I don't know if you're seeing it, but you're getting lots of congratulatory claps from your fellow BDSI members. So hopefully you're seeing that. All right, awesome job. So then, no questions. Let's data mining. Why don't you step up and show us what you've been working on?
All right, hello everybody. We are the data mining group. Here are our members, and we're very excited to show you guys what we've been working on for the past 6 weeks. So first of all, before we get into specific work, let me provide an introduction to our overall goals as a group. Our general goal was to use Twitter data to understand the conversation around COVID-19. We're interested in Twitter data because of its popularity as a platform. It hosts much of the discussion around COVID-19, so there's lots of publicly available data. With this amount of data, though, we can't just sift through tweets one by one to understand the conversation, which is where natural language processing comes in. The data mining group mainly dealt with natural language processing techniques that could help us turn the massive amount of data on Twitter into something understandable. In particular, we use topic modeling, which allows us to extract a number of larger topics from a set of tweets, and sentiment analysis, which allows us to assign sentiments to a given tweet. To this end, during BDSI, we split into groups, and each group proposed methodological improvements to what's currently being done to understand Twitter data, and also proposed more specific research questions about COVID-19. Now we'll move into the individual group presentations, and we should each take around 5 minutes. First off is the group I was in, along with Madeline and Xin Yu. As a group, we were interested in understanding the discussion on vaccines over time with Burt. So our main contribution here is the integration of Burt, which is a neural network-based natural language processing model developed by Google and pre-trained on a large corpus of text data. Using this model, we hope to improve on more traditional methods for finding topics and analyzing sentiments in tweets. And to do so, we fine-tuned our own Burt model with a corpus of vaccine-related tweets. As for our research question, we wondered, how has the conversation on Twitter surrounding the COVID-19 vaccine changed from January 2021 to May 2021? We dealt with 2 main data sources containing COVID-19 vaccine-related tweets, a Kaggle dataset, which contained hand-labeled sentiments of either positive, negative, or neutral for each tweet, and another data set consisting of daily samples of tweets which had any of a set of vaccine-related keywords. We looked at tweets from January and May, and due to computational limitations, only looked at 1% of the larger data set. For sentiment analysis, we split our labeled sentiment analysis dataset into training, validation, and test sets, and applied the Burt tweet model pre-trained on an existing general domain Twitter dataset. We then fine-tuned this model with our own subject-specific dataset. Prior to fine-tuning, we obtained an accuracy of 59% and a macro F1 score of about 0.51, while after tuning for 4 epochs, we achieved 74.8% accuracy and about 0.66 macro F1 score. So given that these are two metrics for measuring the performance of classification models, we can see that the trained Burt model significantly outperforms the more traditional sentiment analysis models. From here, I'll hand it off to Madeline to discuss our results with respect to our original research question.
So when looking at our original research question, we calculated the proportion of tweets for each sentiment in both January and May, and we plotted it as follows. We found that the sentiments for the COVID-19 vaccine on average have not changed very much. In both months, most tweets had a neutral sentiment, and the slight drop in the proportion of neutral tweets between the 2 months is a difference too minor to read into. However, this result is still interesting because we had expected there to be a much more drastic change between the months of January and May due to wider vaccine availability in May compared to January. It could be that there isn't much of a difference because the focus of tweets was often dominated by events specific to that month, which we can consider to be random noise. And since there is bound to be both positive and negative news and events about COVID-19 vaccine in both January and May, this could be why we don't see as much of a change. And then when examining differences in tweet sentiments from both months for specific countries, tweets from Canada had a significantly higher positive proportion of sentiments in May compared to January. And for India, tweets had a significantly lower positive proportion of sentiments in May compared to January, which is likely due to high COVID-19 case numbers and also lack of vaccine availability. And then moving on to examine how sentiments are related to topics within COVID-19 vaccine tweets, we took 2,000 tweets from a Kaggle dataset and hand-labeled them into 7 big topics that encompass the majority of the tweets. We also included a noise topic for irrelevant tweets and then an others topic for any tweets that didn't fall into one of the main categories. These topics were time independent and not related to any specific events happening. This graph on the right shows the set of labeled tweets projected into a UMAP plot, and they're color based on their actual assigned topic label. We see here that there's a mix of different colors in many different regions, but there is some modest grouping of certain topics together. This is because Burt was trained on the task of masking, so the semantic textual distance does not necessarily reflect the fundamental difference between topics. This level of mixing is one of the challenges of using unsupervised clustering algorithms to model topics, which Judy will discuss more in our conclusions.
Thank you, Madeline. So in summary, we deliver 2 main messages for quality data mining from Twitter data with a large common theme. In our case, which is COVID-19 vaccine. So first of all, we found that for sentiment analysis task, label data is essential for achieving credible results. Even ready-to-use models pre-trained on other general domains may perform very poorly for your specific task. However, a small amount of effort within domain training can lead to substantial improvement. Because data mining tasks can easily scale up to millions of samples, even a small percentage of improvement can be extremely valuable. Therefore, we suggest that we should always obtain a small set of in-domain label data if possible. Secondly, for topic modeling, we found that the embeddings of sentences may be more important than clustering algorithms. So as we saw in the last slide introduced by Madeline, when the embedding of sentences is sloppily done, in this case, a Burt model trained on another task, which not necessarily reflects the nature of our fundamental goal of topic modeling, the resulting high-dimensional representation of all the sentences are mixed together. Therefore, it is very difficult to achieve good clustering results, despite how clever your clustering algorithm might be. In summary, in our future work, we plan to propose robust workflows fixing this problem, but for the interest of time, I will omit the discussion, but I am happy to chat after the presentation. Thank you.
Hi, everyone. So for the second subgroup, that was Daratanista, Jacob, and I, and we investigated tweets on COVID vaccination as they relate to colleges and universities using information on vaccine acceptance, as well as the sentiment of the tweets. So in the next slide, we have our research question, which is, what are the themes that we can identify in tweets on COVID vaccination among people with differing sentiment and differing opinions on the vaccine? So to investigate this, our focus was tweets on the vaccine that also had the keyword college in them. And then in terms of methodology, we wanted to find a way to incorporate the sentiment of our tweets as well as the vaccine opinion into clustering algorithms. Next slide for our methods, just to give the bird's eye overview of our methods and workflow. We first labeled the sentiment of our tweets. We next labeled our tweets according to their opinion toward the COVID vaccination. And then we finally performed clustering. So to go into more detail on all this, I'll hand the floor off to Tanista.
I'll briefly describe our workflow. So we collected filter data from June 15 to July 13 using the keywords college and vaccine. After that, we did some partial cleaning like removing duplicate tweets and removing announcements. After that, we did some sentiment analysis using better and assigned labels of positive sentiment and negative sentiment to each of the tweets. And then after some further pre-processing like removing stop words and stemming, we formed a document matrix. Then we hand labeled about 1,000 tweets from our data and assigned labels of positive vaccine attitude and negative vaccine attitude to each of them. Then using this set as a training data, we used a random forests model to assign labels to all of the tweets in our data set. Then we formed 4 different subsets from our data. These were negative sentiment anti-vaccine, negative sentiment pro-vaccine, positive sentiment anti-vaccine, and positive sentiment pro-vaccine. Next, we did clustering in these 4 different subsets. So for the smaller data sets, we used chemidoids. And for the larger subsets, thanks to Juju's thesis, we used a toolkit called Monocle 3, which is used in single-cell RNA sequencing. We use this recursively on the larger data sets to get more meaningful clusters. In the next slide, we have provided a flow chart of the different stages of data preprocessing. So we started with about 10,000 tweets and came down to about 3,200 tweets. Now Darren will speak about some of the results that we got from our data analysis.
Here you can see some of the themes that we found within our subgroups. One thing to note is that sentiment of a tweet usually didn't line up with whether a tweet supported vaccines or not. Something we noticed was that many cluster themes often correspond to specific events that occurred in the past week. In general, both anti-vaccine groups had tweets discussing the side effects of vaccines. Themes about state policies on vaccine mandates or passports were often clustered by the name of their respective governors. We also found that there was some conversation going on between the different subgroups. For instance, there was a boarding school in Australia that received vaccines earlier than they should have, which generated multiple tweets on the event. And Jacob will talk more about this on the next slide.
So yeah, as Darren said, a lot of the tweets or a lot of the events or the topics kind of clustered within one or two of the groups, but sometimes they clustered in different groups as well. So in this example, in this case study, it shows how people who are all tended to be pro-vaccine had very different opinions on this boarding school incident. So there was a boarding school where grade 12, about 150 students got the vaccine early. And in Australia, people under 40 generally couldn't have gotten the vaccine when this event happened. Some people were happy about it because there were a lot of Aboriginal students at this school. So they thought it was a good way to get some minorities people to get the vaccine. But others thought that it was just an excuse to help get rich students who were too young to get the vaccine legitimately to get the vaccine. So I think this is just a good example of kind of the conversations that you can see using our methods. So I think overall our methods were pretty good at classifying into groups, so we could then use that to see which events people were happy about or sad about, but there were some limitations in our method as well, as we can see in the next slide. We only queried tweets based off of the word vaccine and the word college, and college, for example, doesn't necessarily mean university everywhere. In Australia, it also means some high schools or boarding schools, right? So that kind of turned our research question to, kind of guided it into a different direction. We also made labels for our training data set on just what we had, so it might not be able to be used more broadly. So maybe a more diverse training set could be better if we wanted to use this in different situations and reproduce this. There's kind of a small data set as well in the end, and we also don't know if this is reflective of public opinion or just if using Twitter data just shows the polarizing opinions. Also on the right here, you can see an image that is related to the case study I just said, and our analysis completely ignores these types of things. But yeah, I think overall it was a pretty decent method, and we got some really interesting results. I'll now hand the floor over to group 3 to talk about their methods and research.
Hello, hello. So our topic today was vaccine trust in incentivized versus non-incentivized states, and our process improvement was using topic modeling with synonyms. And so as you go on to the question here, just to formally define it, it's how do the topics and sentiments on vaccine trust differ between states with and without vaccine incentive programs? So if we look at our data set here, we collected 20,000 tweets from the API. Next slide, please. 20,000 tweets from the Twitter API between May 16 and June 19 with the keywords vaccine and trust. And we split data by statewide vaccine incentive policies as of June 3rd, 2021. However, 6,000 tweets were ultimately used because they had actually a location tag and it wasn't blank. Moving on to our pipeline, there's a lot of stuff going on here, but the key thing to talk about here, specific to this slide, is that the first pipeline with topic modeling required more pre-processing simply because it used more of a bag of words approach, whereas the sentiment analysis required sentence context and thus had more minimal pre-processing. I'm now going to turn it over to Sasha, and she's going to talk about more about our synonyms method.
Hi everyone. To implement synonyms into our analysis, we developed a 4-step process. First, we performed initial clustering on tweets using k-media-weights clustering using a tweet distance metric based on word co-occurrence in tweets. After this, we found the feature words of each cluster using term frequency inverse document frequency analysis, which evaluates how relevant a word is to one cluster in relation to that word's frequency to the entire corpus or all of the clusters. To make our final collection of overall top words, we use the top words from each cluster that were not found in the top words of any other cluster, so only unique top words. After this, we found the synonyms of all of these top words, and if a top word synonym is found in a tweet, then we append that top word to the end of that tweet. Finally, we stem our tweets, that is, we reduce each word to its word stem because LDA topic modeling in the next step of our pipeline performs better with stemmed text.
Okay, so after we have got our altered tweets with synonyms added to its space, we perform a latent Dirichlet allocation topic modeling method, which is used to extract topic from a corpus of documents by extracting feature words and from each topic and assigning documents to topics based on some estimated probability distributions. LDA is better than other clustering methods because clustering methods being partitioning methods can assign single topics to documents, whereas LDA can assign multiple topics to documents, which is beneficial in our case as topics are mostly made up of multiple topics. In the second part of our workflow, we perform sentiment analysis on tweets with minimal pre-processing using the Burt sentiment analysis model, which was developed by our Burt group. So a big thanks to them. And so this is how we get the distribution of sentiment for each tweets in each cluster that we extracted from the LDA. And so for the interesting topics that we have got, I pass on to the next slide.
Here's an overview of our topic modeling and sentiment analysis results. There are many topics here, so I'll pull your attention to a few salient ones, such as general distrust in other people and the vaccine as a common topic, masks as a non-incentive topic, and trust in one's immune system as an incentive topic. We can see that both incentive and non-incentive topics are largely dominated by negative sentiment. And next, we'll further explore the differences and similarities between incentive and non-incentive topics. One thing to note is that these results of incentive versus non-incentive may be confounded with political affiliation. These maps indicate the number of tweets in our data set from each state. If we look at the incentive map on the left, we see that California and New York, which are politically blue states, contribute largely to our incentive data set, and therefore will likely overpower smaller population red states, particularly West Virginia, Kentucky, and Arkansas. And this may confound our results given that those with different political affiliation will likely lean towards particular opinions with respect to politics and vaccines. Like Sasha mentioned before, there are certain topics that only occur in either incentive or non-incentive data sets, and masks is an example of one of these. So the image below shows all of the clusters in our non-incentive topic that have mask as a keyword, and we can see the size of each cluster is based on how relevant that keyword is to that topic. So our large red topic, we've dubbed our mask topic based on the keyword mask and also a random sample of tweets we've looked at. Looking at a random sample of tweets that we have on the right, we can also get a good idea of why masks is seen as a topic in non-incentive, but not in our incentive tweets. Looking at the first tweet, it talks about wearing masks because of distrust in members of Congress or other people. The second tweet talks about wearing masks because of distrust in others. And the third talks about people wearing masks because of a distrust in science or distrust in others. These three categories of distrust are really prevalent in our incentive data set and kind of overpower the other smaller topics and would be pulling these mask tweets into those data sets. On the other hand, if we look at the next slide, we can see an example of a topic that makes sense to be unique to the incentive data set, and that is the topic of immune systems. However, the image here is showing our clusters with bribery because, interestingly enough, a lot of the tweets that were classified within the immune system topic also occurred in the bribery topic. And pulling a random sample of tweets from our most prevalent bribe topic, we can see on the right that a reason for this might be because people have negative opinions of politicians offering these incentives and they see it as bribes. And as a result, they distrust the vaccine further and talk about how they trust their immune system over that. So immune systems is a really interesting point of how topics between incentives and non-incentives can differ in a reasonable way.
Okay, so finally, some of the limitations of our method is that our LDA clustering methods can be affected by mention in tweets, as some topics only consists of these usernames, which becomes meaningless as a cluster. Also, LDA is known not to perform best for small text documents, for example, tweets, which have fewer number of words. Also, the library WordNet that we use for adding synonyms at the base of the tweets are not advanced enough, and it can cause problems like the word lie were replaced by the word prevarication, but not dishonesty, deception, etc. Also, broad topics that we derive from LDA contain mixture of subtopics and sentiment. For example, the topic mask had discussions which included complaining that others aren't wearing masks, not wanting to wear masks because of vaccination, and etc. And also, like our college sentiment group mentioned, that negative sentiment and positive sentiment should not be mixed with anti-vaccine or pro-vaccine mentality. So in our next slides, we move on to some of the lessons. Okay.
Yeah.
Just before.
And then I guess the last part here is we didn't have time to show all of our results today, but we've left this link to an RShiny app and some CSV files for you to play with and for you to kind of look at the results for yourself. One thing to note is because it's a free plan, you're not going to be able to run the full data set, unfortunately, which is really frustrating. But I'll put some smaller data sets on there too later down the line. I also just dropped it in the chat.
The data mining group as a whole learned some really interesting lessons. Specifically working with Twitter data, we learned it's really important to pre-process our data to get rid of URLs and hashtags. We also, as mentioned in a couple groups, saw that a lot of the topics focused on time-specific events, so collecting data at different times shows different results. Another thing is that extremist views tend to overpower the conversation, and that it was really important to split our time between looking at aggregate information like keywords and topics and between looking at the actual contents of every tweet.
We also had a lot of interesting things we learned about data mining research in general. So we found that you can have some really awesome methods and really accurate results, but if it takes forever to run, it really is not that useful. So we learned that. We also learned we need to make really good readable and well-documented code, since we used each other's data and research questions and methods and kind of played around in different combinations of that. So it became very important for us to be able to do research that other people can use. And since we were kind of had an open-ended question, we all became quite comfortable with trial and error at the beginning of new research and just exploring different directions. So we did learn a lot of stuff generally for data mining research.
And as a final note, we wanted to thank our project assistants and mentors, Dre, Heather, and Johan, and thank you for your attention.
All right, well, thank you to the data mining group. So Excellent job. Very cool. I've never seen anybody create a public link there to have some data that others can use. That's a very unique aspect. So that was very cool. Any quick questions for the data mining group? Who thank you also for staying very much on time. Any quick questions?
Yeah, I just had one question. I was just intrigued by all of your work, and both the groups, you were just amazing. And in learning a completely new data type and topic, just my own personal curiosity, did you see any change in the sentiments depending on the type of vaccine, mRNA versus like, J&J, or AstraZeneca? Did you study that at all? Did the name of the vaccine or anything come up in the tweets?
The name definitely did come up in the tweets, but we didn't specifically examine it in our subgroup, at least. That would be interesting to look into further for sure.
Yeah, actually, in some of our topics also, we did see mentions of those names for big pharmas, and there were mixed sentiments towards these vaccine ideas. So yeah, we did get some mixed sentiments towards these things.
Mm-hmm. Thank you.
I would also add that there was a bit more negative sentiment towards J&J, particularly because of the scare that happened with women who took the vaccine.
Exactly. That's what I was thinking, because there were pauses and so on. So there were sentiments around that. Thank you.
All right. So we're doing pretty good on time. Do you want to stick with a 10-minute break? We're due for a break. Do you want to stick with the 10-minute or? Yeah. Okay. Absolutely. Yes. So we will reconvene at about 2:12-ish. That sounds good.
Yep. Yes.
All right. Take break. And who's up?
I think
EHR.
Whoa. Yes. Electronic health records. You're on the clock, but Bramar, go ahead.
No, I want to thank Zika, Jian, Juju, and Johan for their outstanding mentorship of these two projects. And also to those of you who have put up the BDSI Zoom background, we get a +1. And also thank you for dressing up. Though it's Zoom, I think you all look very fabulous. So I must compliment you on that. So thanks a lot for that.
All right.
Let me know when we can start, Matt.
You ready?
Yep.
All right. All right. So then our third project group presenting for the Big Data Summer Institute Symposium is the Electronic Health Records group. Go ahead.
Hi, everyone. My name is Natalie.
My name is Chris, and we are members of the Electronic Health Records group. Electronic health records are a digitized version of a patient's medical chart and are historically not meant to be used for research purposes. And they include administrative data such as diagnosis, procedures, lab results, and prescriptions for billing purposes. Our research question is, how well can we predict which Michigan medicine patients would be hospitalized during 2018 based on clinical data from 2015 to 2017? Our outcome variable is hospitalized during 2018, which is a binary variable. Either they were or they weren't, and predicting hospitalizations is important for identifying interventions and treatments more rapidly.
Now I'm going to be talking about defining a cohort from the EHR health system. So starting at the top of the diagram, there are 4.6 million unique patients that represent all people that have interacted with the Michigan Medicine Health System. Our intention was to capture patients receiving primary care at the Michigan Medicine by using appointment office visits between January 2015 and December of 2017. We also required a patient to still be alive by January of 2018. Then using this criteria, we arrived at a starting population of about 850,000 patients. And then after this, we extracted variables of interest by crossing starting populations from 4 different separate data sets, which are BMI, demographic data, diagnoses codes, and health system encounters. This slide goes more into what types of variables are in each of the 4 data sets. Starting with the demographics data, it contains a patient's age in 2015, their gender, marital status, race, and preferred language name. The next data set is BMI, which contains all BMI measurements between 2015 through 2017. The comorbidities data set contains binary comorbidities based on the International Classification of Disease, or ICD codes, which classify diseases such as diabetes and lymphoma. And the hospitalization data contains binary variables of whether a patient was hospitalized or not in 2015 through 2018. After merging these data sets and doing some data cleaning, we arrived at our analytic data set. And we also wanted to note that there's a lot of hidden work in this data integration process, and our group spent a couple weeks perfecting this process. This slide goes more into the hospitalizations in the Michigan medicine cohort. So overall, about 3.8% of the cohort experienced a hospitalization in 2018. On the right side of the screen is a scatter plot representing the percent of patients hospitalized by age and is broken down by males and females. From this plot, we see that the hospitalization rate differs by age and sex. And in particular, we notice a spike in the middle of the plot between 20 to 40 years old for females. We concluded that this increased rate is due to women pregnancies.
So to describe our cohort, here are the demographics variables. Here are the number of people with the measurement of the demographics variables. And here is the mean/proportion of the demographics variables. And here is a histogram of age. You may notice the spike around age 20. That is because a college student who is hospitalized is more likely to go to the U of M hospital than a non-college student who is hospitalized, which is true about most university towns.
This slide summarizes the most common comorbidities. On the left is a table of the percentage of the males and females in the cohort that were diagnosed with the 5 most common ones. These diseases are common chronic diseases in the United States. And on the right side, we have a heat map showing the correlation between a subset of the comorbidities. We can see that they're not completely independent of one another, with the darker blue dots indicating stronger correlations. Also, we see in the upper left-hand corner in pink that there are numerous correlated cardiovascular diseases. Each subgroup examined a distinct element of prediction analysis based on electronic health records. One group studied the imputation of missing BMI values for improved prediction. 2 groups studied the informative presence of clinical labs as risk predictors. And the 4th group focused on building a parsimonious model based on prediction metrics. And so now I will pass it on over to one of the clinical lab groups.
Hi, everyone. So we're the first subgroup, and we decided to look at the addition of clinical labs as risk predictors of hospitalization. My name is Taya, and my partners are Margie and Claire. So just to talk a little bit about our project motivation, we know that lab tests can be indicative of health problems. So for an example, if a patient has a respiratory pathogen panel taken, this can be indicative of that patient having a respiratory infection. With this, we know that they may also be informative in predicting a patient's likeliness to be hospitalized. However, these lab tests are only taken as needed, so every patient will not have a measurement for every test. And because of this, we had to be creative in our approach in predicting hospitalization outcome. And we believed that knowing the total number of lab tests a patient had would help us in this prediction. And we hypothesized that the greater number of lab orders a patient has, the higher their probability is of being hospitalized. Our specific question asks, what predictive value do clinical lab tests add beyond demographics, comorbidity, and hospitalization outcome data from 2015 to 2017 for predicting the hospitalization outcome in 2018? And in the left lower corner, you can see a snapshot of our lab's data set.
In order to begin answering our question, we first needed to process our data. We merged 96 million lab entries with patients' Michigan medicine data from 2015 to 2017, which resulted in a data set with approximately 835,000 patients. Then we excluded patients who were hospitalized due to pregnancy. This left us with a data set of 815,000 patients, which includes demographic, comorbidity, and clinical labs data. Since we're interested in the predictive value of clinical labs, we created 2 new variables called total labs and distinct labs. Finally, we split our data into a training data set and a testing data set. Total labs is the number of lab orders a patient had from 2015 to 2017, and distinct orders is the number of different lab orders a patient had during this time. To help your understanding of the meaning of these variables, here's a small example. Patient 1 had a basic metabolic order and 2 glucose orders on different dates. So the number of total lab orders for patient 1 is 3, and the number of distinct lab orders for patient 1 is 2. Patient 2 did interact with the Michigan Medicine Health System from 2015 to 2017, but they did not have any labs ordered during this time, or they had labs done at another institution, so we put zeros here for patient 2. Next, we explore these two new variables. The histogram on the left represents the distribution of total lab orders, and on the right is the distribution of distinct lab orders. The extreme measurements are not shown in the plot for clarity. The median of both of these variables is 2, and the mean of each of these variables is higher than the median because the data is right skewed, since some people have a large number of labs. For example, the most total labs any patient had is 4,177, and 206 is the greatest number of distinct lab orders in our cohort.
We then made box plots of the lab variables by hospitalization outcome. So as seen in the previous slide, there were a lot of high valued outliers. Well, we dropped them, but so we did not show them for clarity in these plots either. Now, looking at the core of the box plot, we see that hospitalized patients generally had higher medians, and this is particularly true for the distinct lab orders plot. We built 4 logistic regression models to compare the predictive powers of our additional lab variables. The base model contained demographic and all comorbidity data, and we subsequently added each, as well as both of the lab variables in the next 3 models as shown. A side note is that we attempted lasso enrich to select the best variables to put in our base model, but given the large sample size and having only 34 predictors, there's low model variability, so we're at low risk of overfitting. Since no variables were removed by these shrinkage methods, we retained the full base model. Next slide. In this final table, we see that with each successive model, the AUCs went up a bit. We note a slightly larger increase from the base to the distinct labs model, which is also reflected in the increase of 129 patients who are predicted correctly at a 7% threshold, a value chosen given that hospitalizations are very rare events, since under 3% of patients are actually hospitalized in our original data set. Further, the last model predicted 159 more patients correctly, which makes it worth looking into for clinical resource allocation purposes.
So just to wrap up and talk about some of our limitations and future direction, we were limited in the definition of our total and distinct lab variables. So in the future, we would like to refine these variables by restricting the age in our cohort. And in the future, we would also report the confidence intervals for each specific model. Thank you. And with this, we can pass it to the next clinical labs group.
Hi, we are the other group studying the presence of clinical labs as risk predictors for hospitalization. I'm Natalie and my partners are Elena and Ananya.
So the objectives of our project are twofold. First, we sought to determine if the presence of lab orders would improve predictive accuracy of hospitalizations beyond the demographics and comorbidities data. Our intuition was that someone simply receiving a certain type of lab test may indicate that they're at higher risk for hospitalization. We expected some lab orders not to add any predictive power beyond the comorbidities. For example, the presence of a glucose or insulin lab would likely not add to our model given a pre-existing diabetes diagnosis. This leads to our second objective, to identify a set of specific lab orders that add the most predictive power. And by predictive accuracy, I am referring to the number of correct predictions for hospitalizations, which is computed as true positives plus true negatives divided by total number of patients in the test set. And how our group differs from the previous lab group is we looked at each individual lab order as a predictor as opposed to the total and distinct number of labs taken for each patient.
This next slide demonstrates the workflow of the project, particularly the data and processing steps. In addition to the demographics, comorbidities, and hospitalizations data, we also used a labs data set, specifically the order name column. In this data, there are about 6 million lab orders in total and 2,133 unique lab orders. For data processing, there are a lot of missing data in the lab data set, and to account for these missing values, we made a new data set by dichotomizing the labs as shown in the figure on the right. We replaced the values of patients who did not have a lab order taken with a 0 and those who did have a lab order taken with a 1. After dichotomizing, there are about 2,168 features, which included the labs, comorbidities, and the demographic features.
So with over 2,100 covariates in our data set, we needed a method to avoid overfitting and simplify our model to make it more interpretable. We chose to use the lasso regression technique, which works well with high dimensional data sets and penalizes non-important features by shrinking their coefficients to 0 while still maintaining high predictive accuracy. We built 4 different models, all using the lasso method. First, a model with just demographics. Next, a model with demographics and comorbidities. Third, a model with demographics and labs. And finally, a full model with demographics, comorbidities, and labs. Our process was to randomly split the data into the training and testing sets, 75% of the data in the training set and 25% in the testing set. We then built the 4 models on the training set and evaluated their performance on the testing set.
Since dichotomizing the lab data introduced sparsity, we wanted to compare the differential shrinkage of the sparse lasso regression models. So these graphs show the penalization of the beta values to 0 based on the significance, where each line represents a covariate. As you can see, these display the trends of the most relevant features. Looking at the graph, we can see which covariates influenced hospitalization the most. These are also the first features to enter the model. We can see that lassos that use demographics, comorbidities, and labs significantly shrunk the number of covariates. This means that once we know the comorbidities, labs are in fact less useful, and that there's a high correlation between labs and comorbidities because more covariates shrunk to 0. An example of this correlation is that glucose and insulin levels correlate with lab tests indicative of diabetes. So using these, we found the optimal log lambda values for a shrinkage using 10-fold cross-validation.
So the model that performed the best included demographics, comorbidities, and labs with an accuracy rate of 0.805. And this is about a 10% increase in accuracy over the demographics and comorbidity model, which does indeed indicate that the presence of lab orders does improve the prediction of hospitalizations. This graph on the left plots the ROC curves for each model. And for reference, a perfect predictive model goes straight up and straight right. So the closer the curve is to this upper left corner, the better the model. The area under the curve is another measure of predictive accuracy, such that the value of 1 is perfect, while a value of 0.5 is no better than random chance. The full model has the largest area under the curve of 0.803 and is shown by the purple curve closest to the top left corner, which again indicates that the labs do add predictive power beyond the demographics and comorbidities. Finding a set of lab orders that add the most predictive power is the question we turn to next.
So to address the second objective, we built a base logistic regression model with each individual lab, demographics, and comorbidities to predict hospitalization. So we kept 565 labs that had non-zero coefficients, and these were the ones kept by the lasso regression model. We fit this regression model with each individual lab as opposed to the lab dataset as a single entity to look at the additive value of each lab at a time. And then we created a function to rank the labs based on how much they added to the baseline logistic model AUC. So the most informative lab tests were 14 that had predictive power over the baseline model, or in other words, their AUC was over the baseline model. If you look at the y-axis scale of this diagram, you see that there actually is not a really significant discrepancy between each of the AUCs, which means that there is some correlation in the AUC. So the most significant lab tests are correlated because as opposed to the other groups, we did not take maternity related hospitalizations out of the data set. So a lot of these tests are pregnancy related, and for example, prenatal antibody testing is something that a woman has done before giving birth, and rubella is a rare disease similar to measles that can be fatal in babies. So this is also displayed in the correlation matrix that shows a lot of the maternity lab related tests have correlation. So the value of our research is that identifying the most significant labs to predict hospitalization can be used to reduce comorbidities, prevent future hospitalizations, and select the best lab test for a specific comorbidity, which has huge precision medicine implications. If we could conduct future analysis, we'd compare this to an elastic net modeling to balance feature selection and address collinearity, which we chose not to do for this project because although arbitrary inclusion of correlated covariates is a property of lasso, we're interested in identifying a set of predictive labs, not focusing on whether any specific lab is included in the model. So it really wouldn't matter which correlated labs get selected for inclusion. And we would also want to see how removing pregnancy-related labs in patients influences the most significant labs. Thank you. Now I'll turn it over to the model selection group.
Just going to jump in real quick. Running low on time for the group, so be sure you're efficient as you're moving.
Okay, hi everyone. My name is Alan, and along with Chris and Neil, we're the EHR variable selection group. Our goal is to build a parsimonious model to predict hospitalizations. By parsimonious model, we mean a model that doesn't have many predictors, but still has good predictive power. Why is this important? Well, it allows for portability, which means you can transfer the model to others without requiring them to have that much data. It is also good for interpretability, since having too many variables makes it difficult to determine which variables are actually valuable for prediction purposes.
We chose area under the curve as our metric to optimize in our algorithm. This means we were directly optimizing the predictive capabilities of the model, in contrast to certain built-in functions like step AIC, which instead optimizes a fit metric. We chose logistic regression as our model for determining the model. We implemented forward selection in R to arrive at a parsimonious model. We then compared our model to the full model with all the predictor variables and to the one selected by step AIC.
So to arrive at a reduced set of predictor variables, we implemented a forward selection algorithm based on AUC. First, we split the full data set into training and testing sets. From there, we fit a model with only age and sex on the training set and computed the AUC. Once we had the starting model, we added to it each remaining predictor individually and then included in the model the predictor that increased the AUC the most. We repeated this process until none of the predictors increased the AUC by more than 0.002, which admittedly was somewhat of an arbitrary choice. In the table, we have the first 19 iterations of the forward selection algorithm. You can see the order in which the predictor variables were added to the model and the corresponding increases in AUC. Using our cutoff of 0.002, we stopped adding predictors after the 11th iteration of the algorithm. And this seems to be a logical point of diminishing returns, after which any increase in the AUC is marginal. Also, for reference, we've plotted all 38 iterations, the last of which gives the full model, for which the AUC is 0.778 and indicated by the dashed line. At least for now on the training set, our selected model of 13 variables yields an AUC within 0.01 of the AUC for the full model.
That said, one limitation of forward selection is that it does not remove variables once they're added. Perhaps the model is missing some combinations of variables that together are very predictive. To address this potential problem, we took our model, kept 4 variables that we considered important, and then randomly removed 3 of the remaining 9 variables to see if another random combination of 3 variables could improve predictive accuracy. As you can see in the histogram, none of the 1,608 models we ran were able to beat out our model, so we left our model unchanged. Our AUC-based forward selection model seems to be doing well because it only requires 1/3 of the possible predictors, unlike the step AIC model, and its AUC is still within 0.01 of the full models after evaluating with the test set. On the graph, the RLC curves of the 3 models are remarkably similar, further assuring us that the model is both efficient and predictive.
For each model, we found the threshold at which the sensitivity is 0.6. Interestingly, we were able to get a slightly higher PPV value with our forward selection model without having to sacrifice sensitivity.
The last way we assessed the models was looking at their calibration, which gives us a sense of whether the predicted probabilities of hospitalization match the observed probabilities. We can see that all 3 models are quite well calibrated for lower predicted probabilities, But at higher levels, they tend to slightly overestimate people's likelihood of hospitalization, which to be fair is better than underestimating. Like what we saw with the RSE curves and the FIT metrics, our reduced model is similarly calibrated to the full and step EIC models, and thus we sacrifice very little by decreasing the number of predictors.
The main limitation we have is low PPV values. If given more time, we would consider implementing a formal stopping rule in forward selection algorithm rather than arbitrarily choosing a 0.002 as the cutoff and adding more predictor variables to be considered. And now we pass it on to the missing BMI values group.
Good afternoon to all. I am Manipal and my research group partner is Sabi Sharkar, and we have been working on how to impute the BMI values and use the imputed BMI values to improve the prediction of hospitalization outcome. Now, what is the need for imputing the BMI values? As we can see from the pie chart here, around 23% of the BMI values are missing. And since we know that BMI is potentially a very important predictor of hospitalization, we cannot afford to lose that much information. So our primary objectives are that we shall analyze the distribution of demographic and comorbidity variables across complete and missing BMI data. We shall select the appropriate variables for predicting missing BMI values, and we shall use the selected variables for imputing the BMI values with various regression models and machine learning tools. Our final objective will be to improve the prediction of the hospitalization outcome of the patients in the year of 2018 using the imputed BMI values. Now let's take a look at the distribution of age, gender, and obesity in complete and missing data. Here, missing status 0 represents the missing data and missing status 1 represents the complete data. As we can see from the first plot here, the age distribution is quite different in complete and missing data. In the second plot, we can see that the gender distribution is almost the same in complete and missing data. Whereas in the third plot, we can see that the proportion of people having obesity is less in the missing data as compared to that in the complete data. There are various possible explanations for this. Some of them are people having obesity are generally more prone to follow up their BMI values regularly as those are required for their treatment purposes. Another possible explanation of this plot may be the incorrect assessment of obesity status due to the uncomputed BMI value. Now the methods that we shall use for BMI imputation are number 1, linear regression model, number 2, regression tree, number 3, random forest, and the fourth method that we shall use will be multiple imputation by chain regressions. Now let's see how we shall select the variables for imputing the BMI values. Here is the plot of the BMI with age and gender. As we can see, the BMI does not vary that much with gender. However, clearly there is a non-linear pattern of BMI with age. Hence, we thought of including the age square term as a predictor variable and see if it improves the adjusted R square value. Now, Abir will take over from here.
Yeah, so now we predict BMI with respect to these predictors: age, age square, obesity, diabetes, hypertension, metabolic syndrome, weight loss, and depression. We are doing linear regression. So how we are getting these variables? We are getting them by lasso and subset selection. And we also cross-check them by measuring sucrose statistic, which gives us the maximum association between the comorbidity and the BMI values. As already suggested, that BMI is 23% missing and 77% non-missing. So we are dividing the 77% non-missing data in two parts: 80% training set and 20% validation set. We are masking these BMI values. So on the 80% training set, we are applying all these regression and machine learning techniques and predicting BMI values. So to define a measure of closeness between the predicted value and the actual BMI, we're defining this thing, which is called MAIE, mean absolute imputation error, because R squared is not universally applicable. In machine learning models, R squared does not give us results. So to understand which one is the best model, we'll use this MAIE. Now we will use the distribution of BMI across the missing and complete data. We can clearly see the imputed BMI values and the observed BMI values have almost the same distribution, though the observed values have too many outliers. But in the imputed BMI distribution, those outliers are not there because we are simply doing linear regression. Next, we have this table. When we are seeing the linear regression with the H squared term, we can see that the mean absolute imputation error comes down to 3.98, where the adjusted R square increases to 0.53. this is the best model among all the linear regression models. Among the machine learning techniques, regression tree and the random forest, they are doing reasonably good work, but the multiple imputation, which we are doing by mice, is not good because it is increasing the variability. And it is actually good for inference purpose, but here we are not doing inference, we are doing prediction analysis. Hence, mice is not doing that much good job. Now, for improving hospitalization outcome for 2018 patients, we are using the same model, and we're seeing for true BMI measurements, the UC value is 0.602. And when we're using imputed BMI values, the UC rises to 0.614. And as conclusion, we can say that H square is a definitely good predictor for these missing BMI values. And our logistic and our linear regression model is better than the regression tree and the machine learning techniques. Fitting logistic regression models for hospitalization outcome in 2080 with imputed BMI values improves the fit. And by imputing BMI, we substantially increase the number of people in the health system for which we are now able to obtain prediction probabilities. Now, as our future work, we can add definitely more predictor variables from the Michigan medicine dataset to improve the prediction of hospitalization outcome. And we can employ the same method for imputing other lab variables to see the significant improvement. Thank you. And this concludes our presentation for the HR group.
All right, thank you. So in the interest of time, we're going to move straight ahead to the machine learning research group. Start up whenever you're ready.
Can you guys see anything?
Not yet. Yeah, it's visible.
Yeah, we can see now.
Okay, great.
Okay. Hi, everyone. We are the machine learning group, and we were guided by our mentors, Professor Nicola and Anindya. Okay, so the overall goal of our project was really just to improve patient outcomes and allow for better workflow in hospitals. And so we were challenged to develop a method for patient-specific predictions of in-hospital mortality. And so we got data from patients in their first 48 hours of an ICU. And the data came from a hospital in Massachusetts, and we had 12,000 patients in total. And for each of the patients, we got vitals, lab results, and other tests that clinicians deemed important. And so in total, we had 42 variables, 6 of which were not time-dependent variables, and then 36 of which that are, such as heart rate, BUN, and glucose. Overall, in the initial 10,000 patients training data, we had 86% survival and 14% that were not surviving. So we want to use the variables that we got to predict mortality for ICU patients. And this problem has been approached before from a variety of machine learning perspectives, and a lot of the results have been promising. And in essence, such algorithms can allow clinicians to have more confidence in their treatment decisions, and it can also allow for hospitals to reallocate resources to where they can deem necessary. And so we hope to contribute to such models, and in turn, we hope that the timely and accurate detection of people at risk can save lives. Okay, so for the rest of the presentations in the machine learning group, there's going to be some abbreviations that we've laid out here. So HMM will refer to hidden Markov model, SVM is support vector machine, CNN is convolutional neural networks, LSTM is long short-term memory, LR is logistic regression, GNB is Gaussian naive Bayes, and RF is random forest. And then in addition, throughout the rest of the presentations, there will be metrics that are used throughout. So precision will be the fraction of predicted positives that are actually positive. There will be recall, which is the fraction of true positives that are correctly predicted. Accuracy is the fraction of predictions that are correctly classified. And F1 score is harmonic mean of precision and recall. And then finally, AUC ROC is the area under an ROC curve. And then the equations are also laid out here. And so I am part of group 1 alongside Anvit, Alejandra, and Ian, and we used a hidden Markov model in SVM to predict ICU mortality.
Okay, so this diagram illustrates our pipeline. The main idea of our project is to use a hidden Markov model with a super vector machine to predict the ICU mortality. The first step we followed was to pre-process the data. We did an imputation and we worked with time windows to train two different HMMs, one for people that died and one for people that survived the ICU. And then with those outputs and the static variables we had, we trained a super vector machine classifier to predict whether a patient is gonna survive or not. It is important to mention here that we went with this kind of approach because HMMs are highly interpretable, and because usually the machine learning algorithms don't work with time series data, but with an HMM we can use this time series data, and with the SVM we can take advantage of the static variables. Okay, so the variables we used were the ones that had more measurements taken, the ones that are considered with the STAP score, and the ones that we noticed were more common for people that died and people that survived. You can look at the features we used on the screen. For the pre-processing, we created regression models considering ICU type and age, and we used those predictions to impute missing data with a forward imputation. Regarding the time windows, we used non-overlapping time windows by averaging the measurements during some time period that's given as a hyperparameter. Okay, so after the pre-processing is done, we train the HMMs and the SVM classifier. So first of all, a hidden Markov model is just a model that assumes the Markovian property, which says that the future only depends on the present. And it's a model that also takes into consideration that we have unobservable hidden states that actually affect the observations we have. We used a Gaussian HMM, which is just an HMM that assumes that the observations are normally distributed, and that works really well with continuous data. Regarding the SVM, that's just a classifier that separates data using a hyperplane.
So our model uses two HMMs. One was trained on patients that survived their ICU stay, and one was trained only on patients that died during their ICU stay. This way, we could capture the temporal behavior of the vitals of patients who died and patients who survived. So when our model tries to classify a new patient, their time series data is passed into both the HMM dead and HMM alive models. And from here, we can extract a Bayesian factor, which represents how well this data fits with each of these models. And these Bayesian factors are input into our SVM, along with the age of the patient, what kind of ICU the patient stayed at, and the weight of the patient. And then in turn, our SVM predicts if the patient will survive or die during their ICU stay. And we tuned some hyperparameters from all over our model. We tuned the time window size to which our time series variables were transformed, the number of mixtures for both of our HMMs, and the extent to which our SVM was regularized.
Here are the metrics for our model. The cross-validation we used tried to maximize the F1 score. It is important to note that the recall is a valuable metric in the context of this problem. This is because we need to identify the patients who are potentially at risk of dying. Our HMM-SVM hybrid was able to identify 78% of the patients who had actually died. So if we had more time, we would have devoted it to feature engineering, feature-based divisions, potentially on age and ICU type, a wider hyperparameter tuning, and further error analysis would also be helpful, particularly because the recall for ICU type 2, which is cardiac surgery recovery unit, was just 52% compared to 80% for the other three ICU types. As a long-term goal, we'd also like to automatically update the model as new patients are observed. So even though our F1 score was not extraordinary, since this model can deal with missing values, it can deal with time series input, it is highly interpretable, and it has a high recall. This model is useful for resource allocation and confirmations of clinical decisions. Thank you.
Hi, everyone. I'm Felicia, and Maddie, Maya, and I make up Machine Learning Group 2. So the model that we chose for this problem is a random forest classifier, and the random forest algorithm itself is an ensemble of multiple decision trees which we use in machine learning, but also in everyday life, which you can see on the left with the donut decision maker. On the right, you can see a group of 9 decision trees that make up a random forest. And you can see that the majority of the decision trees predicted 1. And so overall, the random forest chooses 1 for that problem. So a couple of reasons for why we chose this model. First, we know that the random forest is a very powerful machine learning algorithm that has been shown to have good performance across many different domains, and is overall just one of the best supervised machine learning algorithms out there. Furthermore, the random forest tells us how important each feature is, which can be important for future applications. And looking at individual decision trees can help aid in explainability and interpretability, which is important for communication with maybe clinicians and hospitals and people who aren't as familiar with machine learning. And so our challenge was applying the random forest to time series data when the algorithm itself inherently is not meant for time series data. And our goal is to provide clinicians and hospitals with a bigger picture of patient survival in the ICU that can help with future large-scale visions for hospitals.
Our first step was to split up our 10,000 patients into 3 different pieces: a development set, a training set, and a testing set. From there, we used development to do feature and window selection. So window selection is a method of combining time series data into smaller chunks, but still maintaining overall time behavior. So you can see in this example, we have 48 hours, which was the block of time we had for each patient. And we split it up into 6 different windows of length 8 hours. And then over each window, we would summarize a measurement from a patient with their various summary statistics. So as an example, imagine we take 6 windows, break our 48 hours into 6 pieces, and then from measurements such as GCS, a patient might have 20 over the whole 48-hour period. We would break up all those measurements into their various time blocks, and then we would take summary statistics over each time block. For example, this third bullet point here, mean GCS1 would be the mean of all the GCS scores taken in the first time window. We also included a general 48-hour measurement for each statistic, so we had a good overview of a patient's data as well as this lower level window data. So then to choose our window size, we ran cross-validation on the development set with various window sizes. So you can see here we did 2, 4, 6, 8, 10, and 12. And we optimized on F1 score produced by the random forest. And you can see here we have this peak at 6 windows, so that's what we moved forward with. We also had to choose which summary statistics to use. So we did, again, cross-validation optimizing on F1 over different sets of summary statistics. You can see 3 examples here, set 1, set 2, and set 3. And performance across all these 5 metrics increases as we seem to add summary statistics. So set 3, the yellow here, is what we ended up working with.
Next, we worked with the 5,000 training data points to optimize our hyperparameters. To do this, we used grid search CV. On the right, we have provided 2 examples of how changing the value of N estimators and max features can change the F1 score. After choosing the optimal values of these and other hyperparameters, we then compared the score of our model to other algorithms to determine how well our model was performing, which you can see in more detail on the next slide.
So here's a bar chart of the precision recall and F1 score of how our model on the training set compared to other machine learning algorithms, including the support vector machine, logistic regression, and Gaussian naive Bayes. And as we can see, our model did perform better than the other 3 models in terms of all of the metrics. And so we continued forward with this model and proceeded to apply it to our 2,500 testing points that had not been seen by the model.
Here is our confusion matrix, and the top left and bottom right are those that our model predicted correctly, and the remaining 2 squares are the false positives and false negatives where the algorithm predicted incorrectly. This provides us with a breakdown of where our model did well and where it performed poorly.
As you can see off to the side are our scores from the test data that the algorithm has never seen. These were our final performance measures. And then on the next slide, we have our ROC curves. The first is based on the whole testing data set, and the second is broken up by class. Classifiers that perform better give curves closer to the top left corner, and as a baseline, models give points lying along the diagonal. This would be if a classifier randomly assigned patients to an outcome like flipping a coin each time it made a decision. The closer the curve comes to the diagonal, the less accurate the model is. Here's just an example of what our model looks like. So this is a decision tree from our final random forest. And this is just to show that the random forest can be broken down into these more interpretable features. So you can see the top 10 features that the random forest decided were the most important. And then you can see kind of how it would split on those features. So in this example, the first split was on GCS max 5, and then it proceeds to do classification based on that. And in this picture, the shading determines the strength of the classification. Overall, we are pleased with the results from our model. As you saw, our model outperformed the baselines. Additionally, we feel that we were successful in our task of trying to incorporate the time series data into our model. Finally, we were able to clearly see which features were considered important, which is something that was important to us. Given more time, we would like to add more features and explore the decision trees in our model more. We would also like to see how generalizable our model is at other hospitals with a different set of patients. Finally, one big idea for future work would be to predict whether or not the patient will be readmitted to the ICU. This can be really beneficial in determining how much space a hospital has and allocating resources. On the next slide are our references. And then thank you guys for listening.
So group 3 for machine learning includes Sabir, Esther, Brian, and myself, Rami. And we are using an LSTM neural network to tackle the problem of predicting ICU mortality, which the previous two groups have introduced. Next slide, please. So why use an LSTM or long short-term memory model? So unlike the last two models, LSTMs are designed to be capable of dealing with time series data. LSTMs are a form of neural network, which means that we can use deep learning to learn features from our large data set. This promises less feature engineering, which is very useful when the people designing a model aren't domain experts, like in this case. RNNs, or recurrent neural networks, are a subclass of standard neural networks, and these networks feed in the output of the current computation as an input for the next computation. This is called working memory or short-term memory, and it is very useful when analyzing time series data because the model actually considers the sequential order of the data and it can remember recent values. Lastly, what makes it an LSTM is the long-term memory. So standard RNNs can really only remember a few data points. So LSTMs have an extra internal state, which can save information and forget information. And this internal state can remember information for an arbitrary amount of time. Next slide, please.
Our data consisted of 10,000 patients. We split these patients into 8,000 for training, 1,000 for validation, and 1,000 for the test sets. For each patient, we aggregated the data over each feature over each hour to have a fixed feature vector size. When a feature vector had at least 3 recorded measurements, we used cubic spline interpolation to estimate the data for missing time windows. When a feature vector had less than 3 but at least 1 measurement, we used forward and backfilling. When a feature had no measurements at all, we used mean imputation. Next, we standardized the features by their z-score and loaded the data with batch size of 64, stratified by the outcome label, and split the features of each patient into 35 time variant features and 8 time invariant features.
So for our architecture, we treat the time invariant and the time variant data differently. As a reminder, time variant data consists of measurements like heart rate and blood pressure, which are measured continuously over the 48 hours in the ICU. And time invariant data refers to things like age or gender that are only measured once. So the 35 time variant features are fed into the LSTM. The LSTM runs as many times as there are timestamps. So in our case, with a total time of 48 hours and a timestamp of 1 hour, the LSTM is going to run 48 times for each patient. Then the output of the LSTM is concatenated with the 8 time invariant features. And then the combined tensor is fed into the first hidden layer, which has 48 nodes. We use a ReLU activation function, and then the next layer with 40 nodes uses a sigmoid function to obtain the final classification. Next, please.
While pre-processing the data, we had to make many key choices. When aggregating the data over time, smaller time windows would include more granular and precise data, while larger time windows would decrease the prevalence of missing data. We decided on using a 1-hour time window. We also decided to use mean imputation for features without any measurements. When we instead tried to represent missing data with an identifier value, such as -1 when all values are positive, the model failed to converge. We decided to standardize the data by z-score. Using min-max scaler to scale the data to an interval of 0 and 1 yielded poor results. Finally, we tried both stratifying by ICU type and stratifying by mortality. Both had similar results, so we just decided to stratify by mortality.
So we also changed a lot of the hyperparameters specifically dealing with the model. First and foremost is a choice of optimizer. We had first used an atom optimizer, but that ended up having strange behavior at our loss function, which is shown in the graph in the upper right-hand corner of the slide. The model started overfitting nearly immediately, as you can see with the validation loss going up since maybe the first or second epoch. So we switched to stochastic gradient descent, and that ended up with a more normal looking loss function, but there is still a problem. You can see in the lower right-hand corner, our model in terms of validation loss flatlined and never really converged. So we ended up increasing the learning rate. We also explored using different loss functions, but we found that binary cross entropy was the best one in terms of results. We also changed the size of our hidden layer, i.e. how many cells were there. And we found the best results with 40 cells. So how did our final model do? You can look at the final loss graph at the left-hand part of the slide. It has an appearance about in the middle of the last two ones in the previous slide. So validation loss goes down for a good bit, then eventually goes back up when overfitting starts. The graph of our F1 scores per epoch is also shown. And we hit about 0.5 F1 score in our validation set. We then applied the model to a test set, which was mentioned earlier by Brian, that was not used at all in any step of our training. And the metrics that we got in this application are listed at the right-hand part of the slide. Most notably, we got a F1 score of 0.451. In addition, what really sticks out about our model is the good balance between precision and recall, which are the same to the 10th place.
In conclusion, our LSTM model outperformed the baseline SVM model, but high efficacy comes at the cost of explainability. Due to limited time, we could not tune as much hyperparameters, and the hyperparameters that we did tune, such as hidden size and learning rate, did not significantly improve our result. Given more time, we would have tuned more hyperparameters such as batch size and window size. And in addition, for future research, we might fine-tune hyperparameters, try additional imputation and interpolation strategies, bidirectional LSTM, and exploring other machine learning libraries. Next. These are our references. Thank you.
Is that the last machine learning subgroup? Awesome. Yeah. Thank you so much. All right. Well, thank you to the machine learning group, also the electronic health record group. So congratulations to all the BDSI members. I know that doing this symposium is a big deal, right? I mean, giving a scientific talk in front of your peers, but also professors and graduate students, it's a little nerve-wracking. It's meant to be a learning experience. I hope that the process, while painful along the way, you learn something about scientific communication. And take a deep breath, and I hope you feel good about what you just accomplished, because you really did accomplish something by being able to present here. So the next thing we are going to do is move to our keynote speaker to finish off our symposium. So we are very lucky to have Dr. Amy Herring from Duke University. So first, just thank you for Dr. Herring for joining us for this remote symposium. We wish we could have invited you to Ann Arbor and done this in person and had a dinner here and afterwards. So Dr. Herring received her doctorate degree in biostatistics from Harvard University. After that, she advanced from assistant professor to distinguished professor in biostatistics at the University of North Carolina. And what I have to imagine must have been something of a controversial move. She went from North Carolina over to Duke University. There she is currently the Sarah and Charles Ayres Distinguished Professor in the Departments of Statistical Science and Global Health Institute, and is also a co-director in the Forge Health Data Science Center. So Dr. Herring, hard to pick out any specific award, but Dr. Herring has received numerous awards for her research and her teaching during her academic career, and was elected as a fellow of the American Statistical Association in 2010. And Dr. Herring, I'm glad to say that you can now add keynote speaker for BDSI Symposium to your impressive list of accomplishments. So thank you for joining us today. And
thanks so much. So Bramar, I may need you to share my screen. I have a brand new laptop and it's very cranky and it tells me I need to restart Zoom if I want to share my screen.
Okay, so do I have your presentation?
I just emailed it to you.
Okay. All right.
Tell me if you've got it. I can always pop off and pop back on, but
no, let me find this.
This is why I got the computer before classes started, but I have not shared my screen since I've gotten it up and running.
Yeah, it's probably not giving you permission or something like that. Like there is a privacy.
Yeah, I changed it in the settings. It just says I need to restart Zoom. So
no, I'm happy to do it. And I just wanted to add to Matt's introduction that what an awesome role model Amy Herring is for all of us. Her research interests really span Bayesian analysis, latent factor analysis, longitudinal data, environmental mixtures, but she has truly been inspirational in terms of her leadership as president of ENAR, president of ISBA, and also in being very vocal and active in many various different domains. So, and to me, Amy has been such a great friend that I have had a lot of fun with. And we share a passion for acting and writing skits. And so we have given joint presentations on how to collaborate effectively by silly skits. And there is a popular demand in the biostatistics community for our performances. So I think that I share a lot of memories and we really grew together in the profession. So thank you, Amy, for gracing this event. So I'm going to try to share my screen and pull up her slides.
Oh, I should apologize in advance. They're animated too, so it's going to be a real pain. But if you can move me along as I need to.
No, that's fine. So
yeah, it's too bad I don't have Piggy here. So we had one skit based on I'll talk about another kind of interesting collaboration. But we did have a skit based on a collaboration that involved head injury, and actually. A pig model is pretty good for that. So we had a Piggy who's a little puppet. He's at home today, sadly. All right. So if you want to go ahead and make that full screen, it should be easier if it'll let you. But this has been really great. I am so happy.
Is it not full screen? Because on my
no, I see just I see the tabs on the left and the directions on the right. So it's not in presentation mode.
Let me see.
But it was really great to hear the work you've done. It was so impressive. So for somebody who's an outsider and didn't see you go through the whole process, it really looked smooth and all the presentations were so well done. I also found the questions that you addressed really interesting. They're really challenging questions, and I said give a round of applause to your mentors for picking out some really interesting projects that they had you work on. So, so that was a lot of fun. I was particularly interested in the last two. We actually have a project here looking at, it's in a hospital in Moshi, Tanzania. And they're really interested in using clinical indicators that are easy to get in the emergency room in order to predict development of sepsis, which is a potentially life-threatening infection. And they're in particular interested in whether biospecimens, which are very expensive to process, make the predictions any better. So I was really trying to learn from you guys about what you're doing on that project as well. So this is great. Thank you so much. So today I'll talk more about maybe big opportunities than you guys talked about the big data. My data that I'll talk about today isn't exactly huge, but I thought what I'd do is talk a little bit about my path here today, and then also walk you through some examples. And so to talk about my path, I went to a really small public high school in Mississippi. So how small was my high school? There were no AP classes. We had a case in which no boys graduated in my senior class with a regular high school diploma. So it was a really teeny tiny place. And then you can forward on the next one, or you can just bring them all up if you want. I went to college in Mississippi. My parents gave me the option of going to college in Mississippi or going to college in Mississippi. And so I picked Mississippi, and I went to Ole Miss, which was the flagship, or is the flagship university there. I was a double major in English and math, which were the two subjects I loved the most in high school. And then when I was a junior in college, a professor who was at Harvard, Louise Ryan, who's now back in her home in Australia, gave a talk on biostatistics in the department at the request of a faculty member at Ole Miss, Professor Dale Bowman, who was like the only woman faculty member, and everybody wanted to be her. And she, so it was really awesome that she went. Unfortunately, I didn't go to the talk because I was taking a class with the chair of the math department, and he said biostatistics was fluffy. And so I listened, and I didn't go to the fluffy talk, but I talked to a friend of mine afterwards. Her name is Claudia, and Claudia told me how awesome the talk was. And actually, we both ended up going to graduate school in biostatistics. I went to Harvard. Claudia went to Alabama, which is where her husband was in med school. One thing not to do is to apply to 2 grad schools, only 2. So I was really conservative, I guess, about not wanting to spend money on that. So I applied 2 places and figured if I didn't get anywhere, I would just stay at Ole Miss and get a master's degree in math and figure out what to do next. But fortunately, it worked out. So, so after I, went to Harvard, I went to UNC, and I spent almost 17 years at UNC. And then definitely in basketball season, it's quite controversial to go from Chapel Hill to Durham. I've never seen a coach of one team in the other town, but that's what I did, and I'm happily here now. So if we go to the next slide, I wanted to spend a little bit of time talking about my early data experiences. So you all are way ahead of the curve in terms of where I was at this time. I had very little exposure to real data before I went to grad school. I did have one experience dealing with data between my finishing undergraduate and going to Harvard. And I was able to get a summer internship with the US Department of Agriculture, which has a National Agricultural Statistics Service, or NASS. And NASS has a field office in many states, not all. I think they've got something like 46 field offices. I was in Jackson, Mississippi, which was close to where I lived. And NASS is really interesting as an organization. They cover, they collect data using over 400 surveys each year. They're surveying things like agricultural production, which is mostly what we did in the Mississippi office, farm labor, and chemical use. So it was pretty impressive what they did. And I was able to watch the process, especially with respect to what was going on in the field there. So if you want to just, I think there might be one more. Yeah. So the state field office, what it did is it did a lot of data collection. And so I was able to participate in that. So actually there's a cotton plant And I went out into the cotton fields a little before the cotton got to that stage and was tasked with counting how many cotton balls were on each cotton plant in the sample that was randomly selected in a field. And the state field offices were really interesting. The charge was they were supposed to provide unbiased information for use in production and marketing decisions. And I'll talk on the next slide about whether it was actually unbiased. So I got to do some cool stuff. So I got to lead training on pesticide protective gear. So they figured that was something I could figure out and explain to other people. I then had to go out in the field on a day much like today, which was really, really hot and sunny, and learned why people don't wear protective gear when you think they would. It was really hot. You're out there all day and nobody wants to wear heavy long pants and a long sleeve shirt when it's 10 billion degrees. So I learned firsthand about that. I saw temporary housing around the perimeters of the cotton fields for farm workers. That was the first time I'd ever encountered things like that, where you think about people crop dusting over the homes of these workers. One thing that was interesting to me was that in the office, the local officials were able to change the estimates from the models that the Washington, D.C. office fit to the data we collected in the field. And so that was super interesting because, one, to me, it just looked like the director of the field office kind of went and said whatever number they wanted to say anyway about the expected yield of cotton in Mississippi. But on the other hand, it gave you good insight into where the model was bad, the reasons for which the locals didn't trust the national model, and motivated the need to know more about statistics and understand how to improve methods. In general, I would say field enumeration is a great way for you guys, if you ever have the chance to actually collect data, a great way to understand where error comes from and how surveys work. And so I can tell you, whatever, back when I was in 1995, when I was in the cotton field in July, this time of day, when I got to a new cotton plant, I was not counting the cotton balls as carefully as I was at 8 o'clock in the morning. And in fact, I started running into things like digit preference, where you look at a bush and it's like 100, it's 100 cotton balls, 120 cotton balls. So you really understand, the value in data and taking it with a grain of salt. So my next data experience after that wasn't until the summer after my first year of grad school. And we had to take a class at Harvard in consulting, and you got matched to people that had interesting data. And I'm sure you all are just really sad that you didn't come to Michigan this summer and get matched to data in Michigan dentistry on braces on cats. But that was my summer project. I was the lead statistician on this study that looked at braces on cats. I met with the investigator. I was really nervous, but also kind of excited. It was actually really cool data. So they had a treatment group and a control group, and they had, in the treated cats, they had some teeth that had braces and springs, and some teeth that just had braces, and some teeth that had nothing. And so there were actually 10 different treatment durations. And they were really interested in how epidermal growth factor, which is increased by the pressure they put on your mouth and on your teeth when you're using braces, facilitates tooth movement. And so I got to use kind of fancy modeling techniques. And this was all pretty rewarding, and I liked cats, and I wore braces, and I thought it was kind of interesting until it came time to write the paper. So I drafted the statistical section of the analysis plan, and then the first author, or the last author as the case was, the senior author sends me the paper. So if we go to the next slide, I get the paper, and here's a quote from the paper. 60 male cats, 1 year old, were divided into 2 groups and further divided into 10 time groups. The animals were euthanized, their heads were removed and immediately frozen in liquid nitrogen. So there's my cat Snowball. I have spared you the picture of the cat in the paper, the poor headless cat. And I think there's even the Iron Maiden that pops up if Bramar will move it. Yeah, a guillotine. But that cat looked just like Snowball here, who was my cat when I was a little girl, about the time I was playing with my Burt and Ernie puppets. So I appreciated Burt there because I did have a Burt puppet I played with. I can't guarantee Snowball was never put in a dress and made to play with Ernie and Burt at some time. But fortunately, he did not give his life in the cat dentistry study. But Last summer, I also had some other projects that didn't involve cat sacrifice. If we go to the next slide, I worked on a collaboration with Angela Lynn and also Louise Ryan, the woman who had given a talk at my university on birth defects. And that's a topic I still work on. And in fact, I talked to Angela just this spring about a question I had on a project related to something that we had done. And then if we keep going down through the bullets there, I had a really interesting project on inter-rater agreement. And so this was a cool study, but I learned good lessons there. It was a study of how often clinicians agree in their diagnosis, and diagnosing a subtype of epilepsy is really complicated. And I found out when analyzing the data that the doctors actually rarely agreed, or maybe not rarely, but they didn't agree as much as you would want them to agree if you were, say, an epilepsy patient. The problem with the paper then was that the raters, who were all doctors, neurologists that specialized in epilepsy, were promised co-authorship to get them to rate 100 patients for free, but we showed they didn't agree. And so then nobody wanted to publish the results showing they didn't agree. We finally did 11 years later. I'd lost track of the data by then and had to do a lot of forensics. So that's a good reason to have good reproducibility practices, because it might be 11 years later when somebody asks you to tweak an analysis, getting to, to finally get a paper out the door. So what I thought I would talk about today is just briefly discuss two applications, not unlike your applications, not as big data as your applications, but walk through some examples and take you through the process of, you've done some really interesting and really complicated applied data analyses here, and with some of the method slant as well. And so what I want to do is take you through that process of getting into a really cool data set, and then realizing that, hey, I don't have all the tools I need. I really need to do some methodological development, come up with some new methods in order to answer the questions that the investigator I'm working with really wants to answer. And so, because sometimes that can be hard to think about, well, what is research like in statistics? If you take it away from the medical application. And so I'll show you how an application such as the ones you all have been talking about today is really fertile ground to come up with good statistical methods questions and mathematical problems. And so really fertile ground in biostatistics is a great place to be for that. So if we go to the next slide, the first study I wanted to talk about is called the PIN study. PIN stood for Pregnancy, Infection, and Nutrition. And I got involved in this study when I went to UNC on the faculty, and it was really great. In fact, I still work with some of these people. We collaborated across multiple departments, including epidemiology, obstetrics, and gynecology. I love the obstetrician so much that I actually asked him to be my doctor when I was pregnant, even though I knew he would see me naked. He was just great, and I trusted him like I trust nobody else after working with him for a long time. Nutrition, maternal and child health, and psychiatry. And the other fun part about this study was that the investigators and all these other disciplines, and me for that matter, all worked with grad students who were doing research in their own fields. And so you really got to be involved with bright young students, some of the best minds that we were training in at UNC, which is a really the #2 ranked school of public health, I think. And so that was just a blast. So the first project I'll talk about, if we go to the next slide, was a study about stress. And so I thought it was interesting because we saw, for example, in the data mining group's presentation, how one topic could elicit sort of positive reactions and negative reactions. And so this is not dissimilar from that. We were looking at events that women reported happening during their pregnancies and whether they caused them positive stress or negative stress. So where this came about was Nancy Dole, who was a staff member working on the Penn study, also earning her PhD, had been looking at how stress was related to preterm birth. And so that's when the baby comes before 37 completed weeks of gestation. And so, how do you measure stress? So that was a really interesting question, because it's not like you can give people a stress thermometer that tells you how stressed out they are. And so they used a questionnaire called the Life Events Questionnaire. It was modified for pregnancy because I think the real questionnaire has questions on it like, have you become pregnant? So obviously they left that one out. And there were 37 events that they were asked whether or not the event occurred. And this type of data is called, as you'll see, graded agree, disagree. So if you agreed that the event occurred, then they asked you, okay, was it a really negative thing or a really positive thing, or just sort of somewhere in the middle? And so for each event that occurred, a woman, or all these pregnant people were women in the study, rated the event as extremely negative, which was a -3, and then it had a 7-point scale. So -3, -2, -1, 0 was no impact, and then +3 was the best possible thing. And so Nancy, as part of her research in epidemiology, was faced with a question, well, how does she characterize stress if she wants to see if it predicts an outcome? Does she just count how many events happened? Does she count how many events happened that the mother said were negative? Does she count how many events happened that the mother said were positive? Do you weight the events by how bad or how negatively they were perceived? And so you could come up with a lot of different summary measures of stress, and there were questions about which one makes the most sense. And the literature didn't have a lot to guide her with making that decision. Previous studies had shown that there could be different associations with preterm birth between positive stress and negative stress. So she did want to keep those two things separate, which is why she used this graded agree-disagree type approach when she was collecting the data. So if you go to the next slide, you'll get an example of some of the data in the actual study. And so here we see counts for each event of how many people had it and how they perceived it. So you can see that for all the events, some women said they were positive and some women said they were negative. So divorce was a little bit surprising until I thought about it. I guess if you're like done enough to be divorced when you're pregnant, it's a positive thing for most people. Marriage, some people thought that was positive. Some people thought that was negative. Engagement was something people tended to view more positively. But then there's some things that could go either way. So a change in the number of arguments, a change in your finance, a change in your eating habits. People tended to put those, as positive or negative, depending on their own personal circumstances. And then even things like death in the family, which you might think would be usually negative, some people did rate that as positive. And you might imagine, if you had a family member who had been ill and suffering for a long time, that sometimes that would be perceived as a positive thing. It also could reflect some confusion about how to fill out the questionnaire, So there was actually death of a spouse that I think somebody gave it to. So it made you wonder, should you refer them for intervention? Maybe they were responsible for the death. But so we had a sample of about 1,500 women. We had 37 items, and they could say yes or no. And then if they said yes, that happened, they told us how stressful it was or what its impact was on their life. So if you go to the next slide, what were the things that we wanted to do methodologically? So one thing we wanted to do was to take into account that these events weren't all the same. So for example, a death in the family is probably more impactful than a change in your eating habits, even if the women gave the two things the same score. In addition, we wanted to allow for uncertainty in the weight. So you can imagine filling out the questionnaire yourself and trying to decide if the change in number of arguments was a -1 or a -2 on the scale. The other thing we wanted to think about was, in addition to some of the events potentially being more impactful than others, like, one was like getting a small traffic violation or something, versus your spouse dying, you can imagine that would be a very different impact. Also, we felt that women could be different in their reactivity. So some women tended to assign very modest scores ranging from -1 to 1 and never getting really extreme. While it seems like if you looked at the data, other women were all like -3, +3, -3, +3. And so they seem to experience really big highs and lows or report them. We wanted to separate the impact of positive and negative stress because there was this thought that negative stress would be worse. And so we developed a model that did all this, and it was a lot of fun. And we built on some models that were already available in the literature, but created something new. So if we go to the next page, I can show you a little bit about what we found. Or here's actually the model structure. So I don't want to spend a whole lot of time about that. I just want to say that what we used is an approach that if you go on to study statistics more, and maybe in fact, I'm pretty sure some of you in your projects did deal with variables that were underlying Gaussian random variables. That's a great way to deal with complicated data structures. And so we had underlying Gaussian variables that represented your sort of underlying positive and negative stress levels. And those would depend on factors related to the woman personally. So because we have all these repeated measures on women, and also to the factors related to the event. And then we had summary measures for positive and negative stress levels. So if you go to the next slide, you'll see that we operationalized this in the model in a way that matched a lot of the epidemiologic literature, just looking at people that had high levels of exposure to either positive or negative stress. First, if we go back to what Nancy did in her dissertation, she sort of had what a lot of people would say was sort of a disappointing result. She didn't see anything that was significant. If we put that in quotes, p-values around 0.1, interval estimates that weren't super wide, but did include the null value. But there were things that bothered her about that model. You know, she didn't like that 3 minor events were considered equivalent to 1 major event. So she was really unhappy with the weighting. And so if we used our model, so if we go to the next slide, one thing that was really interesting to look at was how the different items the women were asked about whether or not they occurred were weighted in construction of our underlying stress score. And so recall in the data, the people in the study assigned a weight from 0 to 3, okay, positive or negative. Or you could just count all the events and then weight everything equally. But here you could see, for example, marriage had a huge score. So this was something that tended to be viewed as very impactful, very much related to outcomes, engagement, change in family closeness. These were all things that had very large positive contributions to the underlying kind of good stress or stress from good things. And then you can see some things that just didn't really have much of an impact on good stress. Okay, so change in recreation, getting separated from your partner because of work, borrowing money. Okay, you can understand why those weren't perceived as necessarily good things. But change in family closeness and outstanding personal achievement, change in number of arguments, these were considered by many women strongly positive. So if you go to the next slide, you can see things that had made big contributions to negative stress levels, and some of them overlap. So some of those, like change in number of arguments, change in family closeness, you know, people tended to feel like those were very impactful, and the women would indicate whether it was a positive or negative impact. And at the bottom again, you can see that some of the activities didn't really contribute much to negative stress, change in eating habits, change in social activities, you know, minor, like a parking ticket or something, minor law violation. So this gave us some reassurance that it was worth our while to come up with a new model and to use weights that weren't exactly the same as the weights that women were restricted to when they were reporting the data. So we go to the next slide. We can see what our results were. So we did seem to show there was a high posterior probability, 95%, that there was an elevated risk of preterm birth among women who had the highest levels of negative stress, but we didn't see much of an impact either way from positive stress. So that was sort of the story at the end of the day there. And so just a few takeaways from the study, if we go to the next slide. It led to a lot of cool things. So even beyond the study, we went on to write a lot of papers based on this pregnancy, infection, and nutrition study. We followed the children. We followed the moms after their pregnancy. We got a lot of grants. And so you may know from your mentors that grants are one way that people in biostatistics departments pay their salary and make their living. So if you have a really good idea, you apply to a grant agency. These are all federal grant agencies in the US, and see if they'll fund it for you and give you money to work on that. And so that was really fruitful that way. And it led to the next project, which is totally different, that I'll tell you about. So the next project, and if you'll go to the next slide, I was introduced, Nancy, who I just spoke about, had a friend at the Carolina Population Center who studied something completely different. So she studied adolescent sexual development in a study called Ad Health. And she had a really complicated research question, and the data structure was really interesting. And so I started working with Carolyn and some of her students, basically because Nancy said, you'll like Carolyn, she's really nice, she's fun to work with. So I won't get to talk much today about our collaboration. We eventually worked on a project that involved a priest, because I was afraid of going to hell based on what we were working on a little bit. So if I have time, I'll talk about that. But if we go to the next slide, you get to work with all sorts of fun people. This is a study that's publicly available. So if you're looking for a project for class, AdHealth is a data set that you can download online with a relatively, simple set of questions. It's a population representative study. It took people who were in 7th through 12th grade in the 1994 to 1995 school year and followed them in now more than 3 survey waves, but I'll just consider data from 3 waves. What was interesting about this study and made it a landmark study was actually it was conceived of as a study about sex, and Congress was strongly Republican and it couldn't get funded. And so they went back and they added health outcomes to the study. And so that's why it's called AdHealth. The original PI of the study was Dick Udry, who is just a wonderful, wonderful man. His wife, actually, Janice May Udry, is a famous author. She wrote children's books. So A Tree is Nice is one of her more famous books. But anyway, they had to be very careful designing this study because they were asking very confidential information of the participants. And they started to worry as the participants got older that people would file lawsuits to get copies of the data because, for example, they asked about sexual partners and behaviors, and they didn't want to get caught up in somebody's divorce lawsuit when they think, oh, wait a minute, we did a follow-up study last year and they asked who you had sex with in the past 12 months. So the ID links were kept out of the country so that it would not be accessible through the US legal system, interestingly enough. And what Carolyn was interested in is when she got involved with this work, a lot of the work on teens and sex had been about pregnancy and about STDs. So things that are sort of perceived, at least by parents, as negative consequences of teenagers having sex. And there hadn't been a lot of work on, what is a typical trajectory of sexual development and maturation? And how does that trajectory vary by things like biological sex or cultural factors? And then in particular, they were interested in how sexual minority status was associated with health outcomes and access to care. So there's really a lot of cool stuff going on in this study. And I'd encourage you to take a look online if you're ever interested for a project. So if you go to the next slide, you'll see more about our question. So Carolyn was interested in the components of sexual orientation that were queried in this study. And I have to tell you, if the study were done again today, they would have much better data, but they had to be careful about what they asked. And in fact, it was viewed as controversial to ask about sexual orientation identity when the kids were in junior high. So in the first wave of the study, they couldn't ask them if they called themselves heterosexual or homosexual. That was considered too taboo to ask about in the study. So there's some missing data by design in the study because they couldn't ask that question. We know, of course, that levels of things like behavior partners are evolve with age. And so what Carolyn was interested in is how the association between different components of sexual orientation evolves with age and by subgroups of interest. So for example, is the association between attraction and behavior different in adulthood than it is in early adolescence? Is the association between attraction and identity changing over time? And so we have snapshots at 3 time points in this population. The mean age at the first snapshot is 16, and then 22, and then 28 and a half. So if we go to the next slide, we can give you a little more information. So here are the questions. So at every wave, they ask them, are you attracted to females? Are you attracted to males? So we have all possible combinations of those observed in the data. They asked about counts of partners. So they could ask how many people they had sex with. They just couldn't ask them in junior high if they were homosexual or heterosexual. So I thought that was interesting. The count data are kind of fun in and of themselves. So you get to see things like digit preference, which I mentioned earlier. Do I really believe somebody had 347 partners? That's very accurate accounting. But you saw all sorts of values. Not necessarily the case that these outliers aren't believable. This was a population representative sample. There were, in fact, sex workers in this study. It's a very large study. So not to say these big values aren't true, these were felt, this was after data cleaning. We have these values. Identity was measured using these categories. You were able to say you were 100% heterosexual or homosexual, mostly one or the other. You didn't have an identity, or you were bisexual. And the relevance of whatever measure you're looking at really depends on the question that you're interested in. So if we're interested in looking at risk of sexually transmitted infections, then we're really interested in behavior. How many partners do they have? If we're interested in depression as an outcome, well, then maybe what we're interested in is people whose attraction doesn't match their number of partners, of each gender, for example. So the relevance of the measure does depend on the outcome that you're interested in from a health perspective. So if you go to the next slide, just to give you a little bit of data, this was the fraction, each person is 1%. Of people who were classified as biological females or biological males. And in this study, they were classified by the school. So they were not able to self-specify their gender. This is just biological sex, as the school had it on the record. What percentage said they had any indicator of minority status? So they were attracted to the same sex, they weren't 100% heterosexual, or they had a partner of the same sex. And you can see that increases with age and increases more among women in the study than it did among men. And if you go to the next slide, you can see what's defined as sort of a stricter definition of sexual minority status, where they said yes to all the indicators. So they were attracted to the same sex. They also had partners of the same sex, and they identified as not heterosexual. So pretty in line with what we expect. So we needed a flexible method here, coming back to the data, to just look at, how the association between attraction and behavior changes with age, how it changes by gender. And so we'll look at, or biological sex as it's measured here. So we'll look at both those things today. Then they were also interested in whether that association changed as a function of education or as a function of race. And what we saw there was that there were sometimes differences in the means across race and education. So, you can imagine there might be, for example, if you looked at within race in the data set, most of the time, boys reported more partners than women, but that was not all the case for all the races. Or sometimes, you would see some changes in the mean, but what we're interested in today is the variance, basically the covariance between these things, or correlation. And so we only saw changes in the correlation over time as a function of biological sex and age. And so we'll focus on that. These data are complicated because they are on mixed scales. So the partners are a count. The orientation identity is a nominal variable with a lot of different categories, attraction or multiple binary variables. And we also had weights. And so AdHealth is a population representative study. And so they oversampled some groups in order to have better inferences. So for example, they downweighted majority populations, and they took fewer members of majority populations and more members of minority populations so that they would have more precision in those groups. And there were also some other things they oversampled on. They had a twin study. They were very interested in disabled youth. And so they oversampled groups on those grounds as well. Okay, so if we skip, I'll probably skip through a good bit of the methods just for reasons of time, because I'd love to have a little Q&A. So if we just skip through a couple of these, we developed a model, we used underlying normal variables. We could just kind of skip through this and get to the meat of it, and I can tell you what we found. But the model did allow us to look at how a covariate like biological sex affected the mean response in partner counts, but also the association between different types of outcomes. So this paper, if anybody's interested, was in Journal of the Royal Statistical Society, Series C, or Applied Statistics. So if we go to the next slide, I think that's where the results start. Yeah. So we're measuring concordance in this study using a measure called Goodman and Kruskal's gamma. You can think of it like a correlation coefficient in the sense that it ranges from +1 to be maximum positive association and -1 to be negative correlation. Okay, and I was very conventional in the colors here: blue are boys, pink are girls. And if you look at the left panel, this is attraction to the same and opposite sex. And so as you might imagine, there's a negative correlation there. So attracted to same sex, less likely to report also attracted to the opposite sex. What we see in this plot that we see in a lot of other plots in this data is that the association is stronger for men than for women. So the boys, if you look past age 20, are completely separated from the girls. There's no lavender where they're mixing. So they tended to have more extreme responses and extreme associations between the variables, and the women tended to be a little bit more fluid in their associations. And you can see there's a lot of variability at the end of the age range because those were the very oldest kids in the study when it started. So that's why we have bigger interval estimates at the low end and at the high end, because they were on the edges of the age range. That might be a kid that failed 2 years of high school and was in 12th grade when the study started, kind of thing. And then on the right, we can see same-sex and opposite-sex partner counts. And this is interesting for a different reason. So you might think that these would be negatively correlated, because for sure, attraction, we saw negative correlation. So why don't we see negative correlation for partner counts? Well, one, we do in the boys, but we don't in the girls. And when we got this result, I started checking my programming because I thought I must have made a mistake. Why would we see something so different? And so it turns out when I talked to Carolyn, embarrassed because I must have made a mistake, she took one look and she said, oh, this is exactly what we expect based on the literature, that among women, if you have more same-sex partners, we would also expect you to have more partners in general. So more same-sex partners might be associated during that time with other risky behaviors, okay, or behaviors that may seem maybe a little bit non-conventional. So she expected anybody that had a same-sex attraction who was a woman to also have more opposite-sex partners, which I thought was really interesting. And if we can kind of flip through the other slides, they're basically showing the same kind of thing. It's just all the measures we have. So if you go to the next panel, you can see opposite sex attraction and partner count. So those are positively correlated, more attraction to boys, more boy partners, more attraction to girls, more girl partners, depending on your sex. Same thing with same-sex attraction and partner count. You'll again see the boys are more extreme. So they're up at the top with a stronger correlation than the women had in the study. And then we can skip through the last couple. This is just more of the same things, telling the same kind of story. So for girls, more partners was a little more unconventional than for boys. So this is just a plug for the AdHealth study, which is really interesting, and the data are made available to everyone at the same time. So it's not even like the people who run the study write their papers and then a year later make the data available. They have a data release to everybody at the same moment, which is pretty neat. We also, in the course of this work, Carolyn had a student who was interested in predictors of loss of virginity. And so we were working on that paper, and we ran across some people who said they were virgins, but they had children, and biological children. And so for that analysis, we just sort of assumed they were errors and deleted them from the data set. And then we went back a few years later, and there's a journal, the British Medical Journal. This is worth reading. It comes out, they have an issue that comes out on Boxing Day. It's called their Christmas issue. And they publish fun papers. And so our sort of fun paper was looking at, well, what's a predictor of saying that you're a virgin who gave birth to a child? And so we didn't have everything we'd want to have to look at that. It was a little bit tongue in cheek. We could look at things like, was there a timing of the year effect? Was there an effect of religion? Was there an effect of part of the US? And we definitely saw some of those things, not the time of year, but we did see effects where girls in the South, girls from who followed religions like, Protestant religion, for example, were much more likely to report this than other girls. So we did see some interesting trends in that study. And there were some, but very much fewer boys actually that reported the same way. So we almost have enough of them to analyze now to see about the virgin dads, but it wasn't all measurement error. There were patterns there that influence people's reporting in interesting ways. So just a few closing remarks before we have time for questions. I just wanted to encourage you to continue to take advantage of opportunities like the BDSI. It's a great way to discover what you're passionate about or what you're not passionate about, and to gain really great experience. It's totally amazing to have these close interactions with people like Burt, who I have to say is really, even though it sounds cheesy, a hero of our health system right now for all the work that she's been doing in India. You know, I talked to a Duke student who was sitting in a coffee shop and in Beijing, and there was a student working on statistics, and they started talking about statistics. And somebody in Beijing had heard the name of his Duke faculty mentor, and he was so excited. And the faculty at Michigan are the same way. These are people that are internationally recognized, and it's great that you have a chance to work with them. The other thing I would say is to take advantage of your undergrad time, if you have some left, to strengthen your skills. You know, don't be afraid to go beyond your comfort zone to master something that you think is going to be helpful for you. So, you know, nobody really cares that much about your GPA, to be honest. Maybe your med school application does, but I think it's much more important to get a skill, you know, higher level computer programming skill, even if you're scared of the class. Take real analysis if you think you might be interested in grad school, even though it's kind of scary. You know, be open to doing these things, and really it's a lot easier to learn something when you have a class than when you're trying to pick it up outside of school. Then other things, you know, there are lots of different flavors of jobs or even of graduate programs that match your skills and interests. So I encourage you to ask a lot of questions of people and not to be shy to ask people questions about how they got to where they are, you know, from where they started. I think that's all really good. I think you could probably go on through the rest of them, Vermar. So, you know, really, one other thing I did want to say, there are clubs that you may be involved with in undergrad, like an honor society, a social fraternity or sorority. You know, my niece got a scholarship for grad school from the NCAA, even though she wasn't like a fabulous, I mean, she was a college athlete, but she wasn't like winning NCAAs or anything like that. So there are all sorts of organizations that will have scholarships for grad school that you should look into if you're thinking about that. You know, it could be $1,000 or $2,000 to help out with your expenses. Professional organizations like the American Statistical Association are usually really cheap for students to join, but offer a lot of return on that investment through, you know, workshops and other opportunities, publicizing things like the BDSI. And then just, don't be afraid to ask questions of people. People are usually in our field in statistics, I've learned, and in data science, very willing to help and open to chatting with you. And that's all I've got for today. Thank you so much, Vermar.
Yeah, thank you so much, Amy. I think that was a fabulous talk, how you talked about your data journey and building on small but intriguing projects, but there is sort of a theme gradually emerges and which becomes sort of like, you know, this flickers of things coalesce and become a new luminous body of work. And you certainly have contributed a lot to this field of perinatal, neonatal epidemiology, as well as birth cohort studies. So thank you for all your work and encouraging the students to ask questions and be proactive in their careers. So students, the floor is yours. You heard the journey of an outstanding statistician. And so please feel free to ask any questions to Amy.
And I can't see everybody on my, let me see if I can switch my screen so I can see. Oh yeah.
You can go to gallery mode, yeah.
Yeah, I've got it. Any questions?
And when you ask your questions, just please say your name and your institution. Yes, Julian.
I see a hand up.
Yeah, Julian, please go ahead.
Yeah, hi, I'm Julian. I'm a student at Stanford, but I was wondering, when you were transitioning into roles where you were kind of like the statistician who's working on this applied problem, what was the process like, I guess, catching yourself up to speed with these like subject specific issues? And like, what did you find helpful in doing that? Like in terms of reading papers, listening to the people who are already in that field, or I guess, could you speak on that a little bit?
Yeah, I mean, in some sense, it's like all of the above. So, but some of the things I felt like had a really good return on investment is I was involved with several teams that had weekly meetings, and just going to that meeting and listening to people talk, I thought was really helpful in picking up things in the literature. At first, I thought it was a total waste of my time, and they would spend hours talking about the stupid refrigerator, it seemed like, and I stopped going to meetings for a while, and I kind of got fussed at and told I had to be at the meetings. And And then one day the refrigerator had thawed, and I started laughing, thinking it's good I didn't miss this day because that could affect the sample integrity. And so we even designed a sub-study to look at what might happen with thawed samples to see if we could still use them or if they had to all be thrown out for the types of assays we wanted to do for them. So another thing, in addition to what you mentioned, reading the papers and talking to people, and I would sit in on meetings, which would sort of be like the grad students reporting on what they're doing. So they were helpful because sometimes they didn't know a whole lot more than I did about the subject matter because they were learning, is going to conferences in other fields, and so there, you didn't so often meet a statistician, though sometimes you did, but you got to walk around to posters and really get a sense of, what are the problems in this field? What are they struggling with? Like one thing they're struggling with in perinatal epidemiology, and actually a lot of medical statistics right now, is that cut points for things like definitions of diabetes or the definition of a growth restricted baby depend somewhat arbitrarily on race, and so for example, small for gestational age cut points are lower for African American babies than they are for white babies, which means that you could have two babies that are the same size, and the white baby is considered small for gestational age and gets all this intervention, and the black baby is considered adequate gestational or adequate size for their gestational age, and nothing happens to them. It's based purely on the percentiles of distribution, but you can obviously see how that could lead to discrimination in terms of access to healthcare and access to services. And so that's a problem right now people are struggling with in that field. I would have no real idea if I hadn't gone to meetings and realized, oh my gosh, I can't believe that these cut points are different for Hispanic and white and black and different populations. And for a long time, it was felt like your study was crap if you didn't use a racially specific algorithm to define some of these things, and people's thinking has really come around to see how that can be detrimental to a child.
And even I think preterm birth, right? 37 weeks is so dubious. So how to model that in a more flexible way? Mm-hmm.
Yeah.
Thanks, Julian. Other questions? Yes, Zach.
Hi, I just had a quick question on, I guess, kind of the method. You brought up something about how you would find based like kind of regional differences and also like religious differences. I guess my question would be if you were able to like cluster, kind of blindly cluster, if the study was still there, like through a map, would you find, like, what would you suspect you would find, I guess?
Yeah, so that's an interesting question. Actually, we had to pull some of that out of the paper because the journal was worried about people identifying themselves, which I thought was really funny. It was like, would you really read this paper and remember when you reported that you had a baby but you hadn't had sex? We only had very broad demographic information in terms of space. So we did not know the state. We only knew region. And the region was like Northeast, South, Midwest, West. And I think there was a fifth one. So I don't remember exactly how they carved out. I think, I think the Midwest was carved into sort of upper and middle. A little bit. So religion, we had very specific data on, but we couldn't look at, for example, urban cities, urban centers in the middle of a very conservative part, of the country. So we couldn't tell if somebody was from Chicago or from, rural Missouri, because all of that was kind of clumped into the middle. So we didn't have good spatial information. You can get pretty good information in that study, but you have to be sort of like accessing private data in the census. You have to be in sort of a lockdown environment. And so when I was working on the study, it was actually a lockdown environment. It was a room with no windows. But they wouldn't let you take things out of the data center, that were maps, even if they were really smooth. Yeah.
Awesome. Thank you.
Yeah.
Other questions?
What are you all doing? Is everybody going back to undergrad, or there's some people in the transition between undergrad and what comes next? What's the stage of everybody?
So I can give you an overall summary that there are some people who are coming back from last year. They were admitted last year, but the program was canceled. They're already in grad school. So some of them are actually joining the master's program in Michigan. So we have some students immediately coming this fall.
Great.
That's going to look great for the grant. And, and then well, also there are many students who are undergrads. So we have a combination of rising juniors and seniors, which are mostly, but then we have some other freshmen and seniors as well.
Oh, that's great. Yeah, I see somebody's at UCLA. That's Bramar's pesky brother, Sidipto. Not really her brother, but brother in schooling, is out in biostat at UCLA. So it's a good group. Oh yeah, I see lots of places. My nephew graduated from Yale, and I saw on people's online that somebody's from Penn State. That's where my husband went to school. So
those of you who do not know, Amy's husband is also a statistician. And so I wanted to ask this question, Amy, how is it to live in a household full of like statistics conversation? And do you do a lot of, do you talk shop a lot, or is it around like, how is it being in the same profession?
yeah, it's our kids would probably be the best people to answer that question. I think they would say it's really annoying because you do talk shop like shop about statistics sometimes, but also shop about crazy things that happen at work. So so there is they probably know all the bad biostatistics gossip from overhearing it at the dinner table. So that's kind of interesting. Yeah, I just got a text from David. It's good I'm not sharing my screen. He's getting this award next week. And he's like, be sure I tape my acceptance speech. It's really terrible. So so we'll talk about things like that. Bramar can laugh. She knows that David doesn't like to give speeches like that. Oh, a post-bac. We had a post-bac when I was at UNC. She was really great. So yeah, so it is a little, sometimes it's a bit much. And then when I went to Duke, I was worried it would be a bit much. And I think right now with COVID, it is a bit much. Like, I think we're both really ready to be back at work. So we're not like sitting in the same place and, always under each other's nose when you're having a meeting and somebody's having a meeting on the other side of the wall, kind of thing. But I guess everybody's getting used to that. So, but yeah, our older kids our oldest went back to engineering. So I guess he wasn't that scarred by the experience. Our middle child's a musician and kind of rejected. He actually went to school in Michigan at Interlochen, which is in northern Michigan. And they had a math placement exam. And we told him he had to take math, like it doesn't matter, but you just have to take math every year. And so he purposely flunked the placement exam so he could be in Math for Dummies. So the little one seems to like math only if it can make him money. So he was doing really well with Dogecoin, but failed to sell it when he should have. So
so interesting life stories. Other questions, students?
Oh, it's great looking at what everybody's doing. Yeah, I have a niece at Johns Hopkins. She's in the med school there. She did her undergrad. She really liked it. ISI. I've never been to ISI. I've always been wanting to go. So maybe if we can get on the other side of COVID, I can get Bramar to give me a tour sometime.
Yes, of course.
To arguably the best statistics department in the world. So
me and my brother from school will be happy to do that.
Yeah, we could stay, if we can stay in his house for more, that would be my dream trip.
Yeah.
Yeah.
That would be the house to stay in. So other questions, students?
Oh, Purdue, another big department that just gave Bramar a really big award, Outstanding Woman Alumna. So that's awesome.
So, I always say that women should ask questions as well. So my female trainees cannot keep silent. Questions, students? I will ask one question. And one thing is like, what you said, biostatistics being fluffy. And we have a lot of students who are pure math. They've studied math because they like the abstraction. I have talked with many students who said that, well, I did BDSI, I understand that this is not for me. And I think that's a good thing, that if you understand that, yes, you really love abstract math and this is not for you. But what is your thought on students who are grappling with this idea of whether biostatistics is fluffy? Does biostatistics always have to be fluffy, or can you talk about the spectrum of things that we do?
Yeah, so that came from my ring theory teacher, which was absolutely positively the class I hated the most in undergraduate. So if you want to give me nightmares, like let me go to a talk where somebody starts talking about groups of rings. And he did think it was fluffy, and it was interesting. So, I mean, I think it's hard in a different way, So I felt like it wasn't that I didn't like theory. It was that I felt like I wanted to see the good that came of what I did in sort of the more immediate term, and I had a hard time thinking about myself working on some proof of some theorem that might not be useful now or for 100 years, if ever. And so for me, it was a little bit about more instant gratification, and in fact, in one project I worked on, which was one of my most favorite projects, it was involved with what we did is we got data on how hospitals were treating babies. They were doing things like giving them prophylactic antibiotics. So let's just give you some antibiotics just to be sure everything's okay. Which can have very negative side effects. And so we were able to give kind of real-time feedback to the hospitals about, hey, you're prescribing too many antibiotics. You need to, remember what the recommendations are of, whatever the American Academy of Pediatrics about antibiotics and babies. So I wanted to do that, but I think there are lots of really interesting problems that are really hard. And there are a lot of questions, like you mentioned the mixtures, and, it's a question of, if we look at a study and we want to know what some chemical in the environment does, to babies or to brain development, or is it associated with obesity? I mean, the reality is if we take your blood, you're exposed to lots of things, and a lot of those things are highly correlated. And it's an extremely hard problem, that honestly, I don't feel like we've made a lot of progress on, really, to try to sort out which of a group of chemicals is sort of the bad one. And so we've been working on some methods to try to predict for new chemicals how bad they might be, and I think that's a little bit more promising. But when you look at something like that in humans, as opposed to in a lab study on cells or sometimes on animals, we're dirty already. We're exposed to so much stuff that I think it can be really difficult to pick out in a large group of exposures that are correlated, what something, is that's maybe driving a response. So I think it's hard because you need common sense skills, you need to have data skills and computing skills, but you also need to be able to think really carefully about the mathematics behind new methods. And so that's really challenging and a lot of fun. And I feel like the other thing that's fun to me is that you work on different topics a lot, so I am involved in a new study of sepsis, and that's really interesting. And it's a disease area I don't know anything about, but then also the statistical methods that we need to use are things that I hadn't been working with before. And so that's really exciting, so you don't get bored. So I really love it. But there are a lot of statisticians that work on hard math too, for math's sake. So we had a faculty member actually, UNC Chen, and he graduated in the US, I think from, I'm not going to say, somewhere in California, and it might have been Stanford, but it might not have been. And he did a postdoc in Switzerland and got stuck in Switzerland as a function of COVID and the government clamping down on Chinese visas. And so he wasn't able to start his job in August of last year. He was stuck in Switzerland, which maybe not seems bad, but seems bad to us when we're supposed to be paying him money and we can't because we can't get him on payroll. And he proved like an 80-year-old open question in math just waiting to start his job, that had to do with geometry. So it really wasn't that related to statistics, but it was something he needed to use in order to get a result that he was trying to prove in statistics. And along the way, he just managed to solve this really interesting math problem. So it's a fun field, and I encourage people to think about it, but also, don't be afraid to take classes in other things. If you think it's, if something sounds interesting and you're not sure, take advantage of the time you still have. If you do have some in undergrad, or get on Coursera, or, a TED Talk or something like that, and try to find out about something else too, because there's a lot of stuff out there.
Thank you, Amy. Yeah. Any other questions for Dr. Herring? Yeah, Shin-Yu, go ahead.
Yes, so based on what you just said, it actually reminds me of an interesting experience I had with a friend. So he was running this kind of simulation OR project with using trying to improve on historical results. And what happens is that, in all those old papers published 10 years ago, they have a lot of assumptions. And when he actually applied it to real data, it turned out that those assumptions are completely absurd, and the real data just doesn't fit at all. So I was wondering, do you actually encounter this a lot in applied projects? And how do you, actually deal with problems or make improvements when you're faced with such situations?
Oh yeah. So I would say that happens all the time. And I review papers. I'm like a stats editor for an obstetrics and gynecology journal. And you see it a lot there, because you see often people who are mainly trained as clinicians, and they think that something's really straightforward, but they're not trained as a statistician. So they don't realize it's oh my gosh, they think they have a continuous variable, but really it's a count and it's mostly zero. And, and so you're really could get the wrong answer if you do something naive. So I think that's one fun thing about biostatistics and statistics in general, is that you do see real life situations where you look at it and you think, wow, the models people are using are really wrong. Like the stock market crash, the last really big one, they had really dumb models for multivariate data and tail dependency in those data because there's not much data in the tail. And so why spend a lot of energy modeling the tail? Well, the reason you model the tail is because it can be devastating if something happens, that's a rare event that tanks the market. And so, yeah, I think it's a lot of fun. I mean, there are always, in any good applied project, I feel like you can sit and learn about the data and be thinking about, oh, it'd be really nice if we had a method that would do this, or that would tweak things this way. And sometimes they're tweaks, and sometimes they're big changes that need to be made. But yeah, it's great you saw that though. It's hard to get to the point where you see things like that, to me. I mean, I felt like when I graduated, even with my PhD, I was really worried about would I ever have an idea, that was my own, and how I would think about what to work on. And I got involved in a lot of projects and realized there was a lot of work out there. So,
yeah. Thank you.
Yeah, thanks a bunch. Well, it's so nice to meet you all. If you're ever thinking about Duke, we have a biostat program and a stat program and a data science program and all sorts of other programs. I'm happy to chat with you. So just shoot me an email. Happy to host you guys here. It's only about 95 degrees today. It's like our first really, really hot day. So we're kind of whiny, but it's a great place to be. And we have a lot of back and forth with North Carolina and Michigan with statisticians, that's for sure. So
thank you, Amy, for your time. And we are already 15 minutes past the allocated times with the clock, so I will not keep you any longer, but we really learned a lot from your presentation, and also in general, your presence in statistics and biostatistics. We're very grateful for that. And the students are very grateful for your time. I know that this is a very busy time for everyone with JSM coming up and numerous things to take care of, but have a wonderful day. And thank you so much for attending the BDSI concluding symposium and being the keynote speaker that you can
thank you.
add to your CV. So
I don't worry, I will. And I was just going to type, but it's easier to say it. Thanks to everybody who said thank you. And I really learned a lot from your presentation. So it was so exciting. I'm so glad I got to see all of them. Just super impressive. And Bramar did not bribe me. You know, I've not been paid to say this, but it's really amazing what you've done. And you guys should be so proud of all your hard work. It's just really great. So I look forward to hearing what happens with all of you and what you go on to do.
Thank you so much, Amy.
Okay.
Thanks everyone for joining. And with that, I think my role is over, and I'll hand it over to Matt and Jenna to conclude the symposium.
All right, well, thank you everyone for attending today. So the hard part is over, your work is over, doing your presentations. So tomorrow we will be reconvening for the final day of the professional development day. So at 10 a.m., Jenna, it's the Princeton Review. So getting some advice on preparing for graduate school, right? Since for many of you, that's your next step in your career. We'll be taking a break after that. And then at 1 o'clock, we will have representatives from the statistics and biostatistics admissions committees. They'll give a little speech on what what they're looking for in different aspects of their departments. I also think this is a chance for you to really bring honest questions about what you can do to set yourself apart over the next year, to make yourself, more than just another application in the stack of applications. So, give it some thought over time, or between now and tomorrow, and bring your questions, things that you really want to know. And this is not often do students get a chance to ask the members of the admissions committee from schools and programs they might be applying to, these kinds of questions in this type of environment. And then, Jenny, do you want to describe the last piece then?
Yeah, so we'll do the panels, and then so yeah, that'll be open Q&A. And I just wanted to add, this is a great time for to ask all those questions that I know that some of you guys have been asking me, and I'm not always the best person to answer all those questions because I'm not on the admissions committee. So all those questions about letters of recommendation, courses to take, things like that, this is a great time to ask them. 2 years ago, these panels were extremely beneficial. And so then after that, we'll take a quick break, and then we'll come back for student remarks and awards. And I'll give you guys some more information about that tonight in my email. And then we're going to have Bramar's journey lecture. So you can look forward to that. It's a wonderful story, and I'm really excited to hear it. Bramar, I don't know if you want to say anything.
No, I'm really grateful for all of your presentations, and you did a wonderful job. And as you saw that in the rehearsal, I was quite harsh to prepare you for this day, and you rose to the occasion, and you did a brilliant job. Tomorrow, again, the admissions committee meetings are very critical, and you are going to get a lot of information that you have been asking all of us. I also wanted to mention that I had a chance to have one-on-one meeting with most of you, but in case like you did not make an appointment or did not get a chance to talk to me one-on-one, and you'd like to do so, because we are on Zoom anyway, things do not have to get done in these 8 weeks. In the coming weeks, if you ever want to talk to me, please do write to Tara or Davina or Jenna, and we'll connect. So BDSI is a launching pad for you. It's not just a sporadic 8-week time that you spend. And we hope that the tomorrow's professional development is going to round up some of the questions that you have. So with that, have a wonderful afternoon, and I'll see you tomorrow.
Thank you everyone so much for coming. You all did a wonderful job on your presentation. And thank you, Dr. Herring, for the keynote lecture.
Thanks. Bye-bye, everyone.
Thank you.
Thank you.